चलो
Can you audible, sir? Am I audible? Can you audible me?
yes.
Am I audible?
Yes.
Hello. Camera. Okay.
Very good afternoon, all of you. Honorable dignitaries of today's conference, HOD of Mathematics Department, Salunke ma'am, resource person, Dr. M.T. Gopne sir, Assistant Professor, Department of Mathematics, Presidential Address, Dr. J.B. Patade, Principal of our college, Dr. V.S. Sawant sir. Very good afternoon, all of you. As you know, today, a workshop conference is here, recent trend in mathematics and statistics. So it's immense pleasure. I would like to inform Dr. A.S. Salunke ma'am to deliver introduction of today's conference. A.S. Salunke ma'am, please.
Very good afternoon to all of you. It gives me immense pleasure to welcome all on behalf of Rayat Shikshan Sanstha's B.B. Bhosle College, Koregaon, District, Satara in Maharashtra. Its Department of Mathematics and Statistics, in association with Internal Quality Assurance Cell, organized National Conference on Recent Trends in Mathematics and Statistics under the valuable guidance of our principal, Dr. V.S. Sawant sir. This conference is expected to create the awareness about the emerging areas in the fields of mathematics and statistics. Also, this conference would create awareness and enrich academic atmosphere in this region. For this conference, three eminent personalities are present with us. First, that is Dr. Sachin Kumar Bhalekar, sir, Junior Scientist, University of Hyderabad, Dr. Phoebe Gute, sir, Solapur University, HOD of Department of Statistics, Dr. M.T. Gopne, sir, from Shivaji University, Kolhapur, Department of Mathematics. I welcome all these eminent persons and also all participants for this national conference. Now I introduce Dr. M.T. Gopne, sir, the chief guest for the session 1. Sir, M.T. Gopne, sir, has completed his BSc in 1999 and master's degree in 2002 from University of Pune. He qualified NET in 2001. He completed his PhD degree in 2013 from the Pune University and PhD thesis entitled Some Aspects of Reducibility in POSITs. He is currently working as an assistant professor in the Department of Mathematics of Shivaji University, Kolhapur from January 2005. He has 16 years experience of teaching to UG and PG students. He has published 5 books: Advanced Discrete Mathematics, Linear Algebra, Numerical Analysis, Advanced Discrete Mathematics, Combinators. His paper is on weakly primary elements in multiplicative lattices, Southeast Asian Bulletin. He worked as a research person for state level seminar held at Pet Vadgaon, 22nd annual conference of SUMS held at Vita, and 24th annual conference of SUMS held at ZER. Sir has presented 7 research papers in international conferences and 6 papers in national conferences. Also conducted 6 national workshops and conferences and attended 15 national and international conferences. Sir has worked as a coordinator of state level Nirmal Gram Inspection Committee, team manager of state level NSS competition Utkarsh at University of Pune, rector Boys Hostel, Shivaji University Kolhapur, stage coordinator Lok Kala Kendra, National Youth Festival, Shivaji University Kolhapur in 10 to 14 February 2017. I request to Dr. B.T. Patade sir, Assistant Professor, Department of Mathematics, Jaisingpur College, Jaisingpur, to chair this session. Now I will hand over this session to Dr. Gopne sir. Please, sir.
हॅलो, आवाज येतोय मॅडम? हॅलो,
Hello.
आवाज येतोय? हॅलो,
Yes, sir, you are audible, sir.
Yes, sir, you are audible, sir.
okay, okay. Make me co-host for sharing the
You are
screen.
audible, sir.
Please make me co-host for this session so I can share my screen. Okay. Screen is visible to all. Hello.
Yes, sir, you are visible.
Okay.
Yes, sir, you are visible here.
Good afternoon to all. Thank you, Salunke madam, for nice introduction. Dear chairperson of this session, Dr. Patade sir, respected principal, Dr. V.S. Sawant sir, coordinator of this conference, Salunke madam, teachers and student friends. It is very difficult to me choose the topic for this session because title is very broad for this conference, and so I chosen this forbidden reducibility title for this talk. First of all, I congratulate the college team for organizing national conference in very short period of time. I think its execution started before 10 days only. It is very difficult to explain any research topic in just 45 minutes, and it is on online mode. The mathematics teaching on online mode is also difficult task for a teacher and students to cope up with the things. Near about last 3 years, students and teachers are doing this online mode. I'll try my best to convey my topic to you in the stipulated time. Every researcher has different approach to see the subject. There are very small group working together for similar topic. Even the guides and research students are in different topics. They are working. Only logical thinking is in the same line. The mathematics person is logically very strong from the other subject person. Before going to my technically of lecture, I want to discuss some basic concepts, and then we will discuss about some part of the research. Mathematics research is not like we are work out some experiment in the laboratory and get some output. For this research, the person have to collect some reasonable material from various things, online, some material available on online mode also, and then we have to analyze it, and then we are thinking about to do some new things according to that. My topic, today's topic is forbidden reducibility. For going to direct forbidden reducibility, I'll just recall some things related to this topic. Most of the people knows partially ordered set. For that, we need one non-empty set and one relation. Under that relation must reflexive, antisymmetric, transitive, and then we call that set as a partially ordered set under that relation. Then for any two elements of that coset, if there exists supremum and infimum for two elements, then we call that structure as a lattice. And there are many types of lattices were studied by various researchers. Some various properties of various types of lattices also studied. Characterizations of various parts of lattice theory were done by various parts of the country and various parts of the world. The research is going on this lattice theory. Forbidden means what? We have to find a structure, smallest structure that does not satisfy some particular properties of that type of lattices. Means on this forbidden structures, various mathematicians studied and characterized forbidden structures for the various lattices also, and the other structures also. It is well known that modular lattice and distributive lattices were studied using the forbidden structures. The modular lattice M3. In the presentation, that M3 structures is also added. At that time, I recall that M3 structure. N5 structure is the forbidden structure for distributive lattices. Distributive property is well-known property. If the lattice satisfies distributive property and its dual property as well, then we call that lattice is distributive. But the structure, when we start with the forbidden reducibility, we have to just forbidden structures. In that concern, we write some statements as well. If a lattice is modular, if and only if it does not contain M3 or diamond structure. Similar way, the lattice is distributive if and only if it does not contain M3 or N5 pentagon. N5 can may be called as a pentagon. Also, this statement is can be revised in the form of a modular lattice is distributive if and only if it does not contain M3. That also the same type of statement. Various classes where we studied regarding reducibility. We have first describe these results in terms of algebraic proofs, and then we studied in terms of forbidden structures. A lattice is reducible. When we call a lattice is reducible, an element of X of lattice L is deletable if L minus X satisfies the same properties as that of L. Means any element, if we eliminate or delete from L, then the structure should be the same type of structure. That is, if I choose the class modular lattice and if I delete X from that lattice, then L minus X must be a modular lattice. The same kind of classes we studied in a different manner. The class is reducible if every element, every stage, we can delete one element and we reach at the just single element. At that time, we can say that class is a reducible class. We have listed some classes here. Modular, distributive, semi-distributive, etc. has been carried out by Bourdaloue and Monjardet in terms of algebraic manner. Then Cayley and Rival also described some forbidden structures related to strong lattice, and that we are using for characterizing the deletable element using forbidden structures to the strong lattice as well as the POSIT. Reducibility also studied in POSIT structure by Khairat and Vapare. And in this short lecture, I have carried out or taken some classes of reducibility in terms of forbidden structures. For that, we need some properties of the element. Join irreducible element is nothing but the unique cover to that element, and dually concept of meet irreducible elements means it is covered by just covers to the just single element. The set of all non-zero join irreducible elements can be written as J of L and respectively meet irreducible by M of L. Sometimes it can be represented as J for join irreducibles and M for meet irreducibles. The element is W irreducible, means it is both join irreducible as well as meet irreducible. The element is in just chain. It is covered by one single element and it covers to the single element. That is called W irreducible element. Here we quoted that result that I have already told you. A lattice is modular if and only if it does not contain pentagon N5, and modular lattice has also been called Dedekind lattices. This Dedekind mathematician discovered this characterization for modular lattice. That's why this can be written as a Dedekind lattices. A lattice is distributive if and only if it does not contain a pentagon or diamond. Pentagon is same as previously characterization for modular, and M3 that is diamond. 5 element, both are the 5 element lattices. This is the basic characterization related to forbidden reducibility. A lattice, any lattice, here is no bifurcation for various types, it's just a lattice. When a lattice remains a lattice, when we delete X, which type of element we delete from a lattice, then lattice will be the becomes a lattice. That characterization is shown in here. A lattice L is L be a lattice and X belongs to L. then L minus X remains a lattice if and only if it does not contain a sublattice isomorphic to the lattice containing X depicted in the following figure. Here, this X is doubly reducible element. It's not a irreducible element of any kind. Means it is a meet of two different element and also join of two different element. That's why it is a doubly reducible element. But we need for this reducibility, either it satisfies one of the condition that meet irreducible or join irreducible, and then we think about the deletability. If we delete this X, this lattice does not remain a lattice because the above two elements directly connect to the below two elements and making a cross, and also this line becomes connected, and therefore we don't have a lattice structure. We do not find the supremum for these two elements and infimum for these two elements. That's why it is a forbidden for. It's the smallest structure containing X. Such type of structure containing another lattice is also examples for the such forbidden structures. I'll just carried out, just outline, I'll explain here. We have to take these 5 elements and 4 elements around the X. X is fixed. The above two we can names as x1, x2, below two x3, x4, and on that we just consider the cases that x1, x2, meet of x1, x2 is x, and join of x3, x4 is x. Then we have 3 cases. X belongs to join irreducible but not meet irreducible. Next case, X is meet irreducible but not join irreducible, and X is both meet irreducible, join irreducible. But in this case, we don't have all these 3 cases, and that contradict to the case that the lattice, the structure forms a lattice. Then we use this result. This J minus means the below J element. We use this result of Cayley for characterizing the deletable elements of strong lattice. This is the characterization of strong lattice with finite length using the forbidden structure. A lattice L of finite length is a strong if and only if it does not contain a special pentagon sublattice of the form represented in the figure below, with J belongs to J of L, means J should be the join irreducible elements, and this is the special pentagon. We have quoted N5. The N5 is nothing but the same structure. We have just specified here some particular element X, J, J minus. 3 elements are the fixed elements here, but in general N5 we do not have any restrictions on these elements. We have restricted these elements because of the characterization of strong lattice. Similar characterization done for strong poset as well by Kharat and Vapare. Using that strong characterization of strong lattice, we have characterized strong lattice of reducibility using forbidden structure. L be a strong lattice and X belongs to L. If X does not belongs to J of L, means X is not join irreducible, then X, L minus X is strong if and only if it does not contain a sublattice isomorphic to one of the following lattices containing X depicted in figure 1 and 3. Figure 1 means it's just the first figure, and figure 3 is the below this. Here J and X are fixed, and double line represent the covering relation, means in between these two there is no element. That is the covering relation between these two pair. The next characterization characterization for modular lattice with zero distributive, means we have combined two classes, modular lattice, zero distributive lattice. These two classes are combined, and we have characterized the deletability using forbidden structures. A modular lattice with zero is a zero distributive if and only if it contains no sublattice isomorphic to D7 or M3 containing 0 of L. That structure is of this form. This is D7, and what is M3? M3 is the above part only. This part is nothing but M3. I'll just minimize the things here. This total structure is D7, and this sub part of this is nothing but M3. These are the forbidden structures for modular lattice with zero distributive lattice. If it contains such structure, substructure, then it does not reducible lattice. Okay, next we have characterized again modular zero distributive lattice with zero. Here we have deletable element when L minus X is zero distributive if and only if it does not contain a sublattice isomorphic to the lattice containing X and 0 depicted in figure 1 means the first figure, and the fifth means the next this. There are again two types, A and B. There are total 3 substructures are there. The first one, this A, and this is B. If we delete this X, this isomorphic to just M3, and that is not a distributive lattice. If you delete this X, this forms a D7, and D7 already we have characterized as a non-zero distributive lattice. For proving this, we have proved the result both way. Assuming M zero distributive lattice implies the structure does not contain these lattices, and converse part, we have assuming the structure does not contain these sublattices, then we have shown the M lattice is modular zero distributive. There is a time constraint, that's why I'm not going to details of these proofs. This is a definition of modular pair. If lattice L, AB belongs to L, we say that AB, ordered pair AB, is not ordered pair, it's just a notation in the form of ordered pair, but it is not an ordered pair. AB is a modular pair with respect to that modularity. There is a condition, ABM is a notation for modular pair if C join A mid B is equal to C join A mid B. This is the condition for modular lattice. But in the definition of modular lattice, we have to have comparable elements. Here for every C less equal B, if this satisfies, then AB is modular. And there in the general modular lattice, we have just 2 comparable elements, then we have such type of condition. We say that dual modular pair as well, that can be just replace meet and join, meet by join and join by meet in the previous equation, and also the order of element. Then we call dual modular pair. Using that modular pair, we have characterized a deletable modular pair as well. We have proved that lattice L be a lattice X belongs to L. For AB belongs to L, ABM holds, means the AB is a modular pair in L. Then ABM holds in L minus X if and only if L does not contain a sublattice isomorphic to one of the lattices containing ABX. Here we have 3 elements fixed. In the previous results, we have just fixed 1 element. In the strong case, we have fixed again 2 elements, join irreducible element and X. And here we have fixed 3 elements. One figure is fixed because that is related to lattice, and that's why that is common in all the results. And these are 2 additional structures for modular pairs remains a modular in L minus X. Here we have characterized some part of distributive lattices. Lattice L is distributive, X belongs to L. L minus X is distributive lattice if and only if it does not contain a sublattice isomorphic to lattice depicted in figure 1, means the first one. And the second figure is missed here, that it is D7. D7 is the common figure, just for marking that is wrong. That's why it makes a question marks there. D7 and the first one. These are the 2 forbidden structures for deletability in distributive lattices. Then we have characterized for joint semi-distributive. Every distributive lattice is joint distributive, semi-distributive, but joint semi-distributive is not a distributive lattice. It's a larger class than the distributive lattice, and we have characterized deletable element in terms of forbidden for larger class as well. L be a finite length joint semi-distributive lattice and X belongs to L. Then L minus X is a joint semi-distributive if and only if it does not contain a sublattice isomorphic to one of the lattice containing X depicted in figure 1 and 7. 1 means the first one, just put the 2 squares one upon the other, and the 7th is containing 5 structures. These 5 structures are the forbiddens related to joint semi-distributive. This double line is nothing but the again covering relation. It must be covered by this element. In that way, we have these 5 forbiddens and the one related to lattice. These 5 forbidden structures, if does not contain in a lattice, joint semi-distributive lattice, then we can delete such X. That 5 and this 3. Total 8 structures are there. Then we have characterization for joint semi-distributive as well as mid semi-distributive, means semi-distributive. A lattice L of finite length, which is semi-distributive, if and only if it does not contain a sublattice isomorphic to one of M3, S7, S7 star, L4, L3, L4, L5. These structures, if any lattice does not contain, then we call that lattice is a semi-distributive. Using this characterization, we have developed a characterization for deletability by forbidden structures. M3 I have not quoted here. M3 is the just we have quoted before, and the list remaining are the here. Then we have characterized forbidden structure for deletability in atomistic lattice. The atomistic lattice means every element can be written as a join of atoms. Join of atoms means atom means the element which covers zero, and such atoms gives the representation for all other elements. Means if here we take these two elements are the atoms, and this third element is join of these two atoms. Any single element is a join of itself. Therefore, we can say that this structure is a atomistic lattice. All these representations or calculations or whatever characterizations we done, that is for only finite lattice or a finite length lattice. This L is atomistic, or L minus X is atomistic if and only if it does not contain sublattice isomorphic to of this form. And the first figure here, B belongs to J of L minus X, means when we delete X, after that this B must be join irreducible in L minus X. In that case only we can say we delete an element from L minus atomistic lattice. Then atomistic lattice with covering property, that is another class of lattice that also characterized using forbidden structure. L minus X is a lattice satisfying covering property if and only if L does not contain a sublattice isomorphic to one of the lattice containing X and 0. Defect in figure 1 means the first one, and 11 is the next figure, where Y is join irreducible element in new lattice. These all double lines saying that the covering relation should be there. There is no element lies between these two elements, these two elements, these two elements, and these two elements. Similarly here Y is join irreducible in the X deleted lattice. These forbiddance makes easy to see if any structure is reducible or not. Otherwise, we have to check for every element it is deletable or not. That makes easy using this forbiddance. These are some references I have quoted and used for this presentation. At the last, I'll just say something. Applications related to this reducibility are started by Lexman and Zariski. They gave applications to the biological processes using Heyting algebra, and that Heyting algebra is a part of this lattice theory. Also, Kharat and Vapare also gave some applications to the biological processes. There are many open areas related to this reducibility. We have just carried out a single element is deletable or not. There are maybe one element is not deletable, but more than one element can be deletable from the structure. In that way, some characterizations are made by Kharat and Vapare, and some of the classes are still open related to this reducibility number. Maybe some of you can choose that topic and make a characterization related to this structures. At the last, I will thank to Principal Dr. V.S. Sawant sir, Coordinator S.S. Salunke madam, for inviting me to deliver a talk in this national conference. Also, I thank all the audience for listening patiently. Yes, is there any questions? I'm ready to answer for the questions.
Anybody having questions, just raise your questions.
Now I request to Dr. Patade sir to give the views of the lecture of Dr. M.T. Gopne sir and take the vote of thanks. Here. Dr. Patade sir. त्यांना unmute करा.
Hello. Am I audible?
Yes, sir.
Hello.
Yes, sir.
Thank you, Dr. Gopne, for a very nice talk on the topic forbidden reducibility. In this session, Dr. Gopne discussed the basic concept of partial order set called as poset, supremum and infimum, reducible lattice, modular lattice, doubly reducible, irreducible lattice, distributive lattice. Also, he explained the graphical representation of strong lattice, zero distributive lattice, isomorphism of lattices. I hope this presentation is very useful for researcher working in this field. Thanks again, Dr. Gopne, for this nice presentation. Also, I thank the organizing committee for giving me the opportunity to chair this session. Thank you. Hello. Hello.
Patade sir.
Sir,
Balekar sir, join this session.
now I take over the charge to organizing committee. Hello, madam.
Yes, sir.
Afternoon, all of you. Now we are starting our second session of the conference. It's my great pleasure to introduce our chief guest, scientist, Dr. Sachin Kumar Bhalekar, sir, Associate Professor, School of Mathematics and Statistics, University of Hyderabad. Sir has completed his BSc with distinction from New Arts, Commerce and Science College, Ahmednagar in 2005 and master's degree with distinction from University of Pune in 2007. He qualified SET, NET JRF in 2008 and GATE in 2010 with All India rank 155. He completed his PhD in 2011 from the Department of Mathematics, University of Pune and honored as Padma Shri late N.S. Venkatesan Gold Medal for the best PhD thesis entitled as Investigations in Nonlinear Systems of Fractional Order in Mathematics from University of Pune. He has worked as the assistant professor in Department of Mathematics, Shivaji University, Kolhapur from 2011 to March 2020 and recently working as an associate professor at the School of Mathematics and Statistics, University of Hyderabad. His research interests are dynamical systems and fractional differential equations. He has published 60 research papers along with 2,814 citations and worked on 4 research projects funded by NBHM, CSIR, UGC and SERB. He has published several research articles with international collaborators from USA, Turkey, etc. Under his guidance, 2 students have completed their PhD and 1 is working. In November 2018, he has honored A.M. Mathai Research Excellence Award from Society for Special Functions and their applications for his excellent research. He has been recognized as one of the top 2% of scientists ranking by Stanford University. He is an editor of a book entitled Frontiers in Fractional Calculus in 2018. He has written several book chapters in some of the reputed books. He has represented his research work in national and international conferences. Also, he has given invited talks in many workshops, seminars, and conferences. Sir has research collaboration with various international universities. Today, we have such a well-known personality in mathematics with us, Dr. Sachin Kumar Bhalekar, sir. It's our proud privilege to have him as a resource person. And I request to Dr. D.R. Fartade, sir, Head Department of Mathematics, Balasaheb Desai College, Patan, to chair this session. Now, I would request to Dr. Bhalekar, sir, to start the invited speak. Bhalekar, sir.
Thank you, madam, for nice introduction. I'm happy to see so many well-known faces in Shivaji University. I'm sharing my screen. Is the screen visible? Yes.
Yes, sir.
Okay. So today's topic is delay differential equations of fractional order. So I will discuss some basic things and then move forward. So this talk is based on some of my papers and preprints. It is work done with my student Deepa Gupta, and one paper is published in 2016 when I was working in Shivaji University. So what are fractional derivatives? First thing, we know that we can have derivative of order 1, 2, etc. That is integer order derivatives, and when this order is non-integer, say 0.3, okay, derivative of order 0.3, etc., then these are called as fractional order derivatives. Now, it is not only the fractional thing, means it is not only the thing of the form, say p by q. Okay, we can consider any real number as order of derivative. Next thing, we can consider complex number as order. Okay, so derivative of complex order. Then we can have order of derivative as a function of t. Okay, so order is changing with time t. Then we can have distributed order derivative and so on. Okay, so many such generalizations are there, and these operators are not local like our usual derivative. I mean, when we want to find derivative of function at some point, say t naught, then it is sufficient to have the values of function in the neighborhood of t naught. Okay, so our usual derivative is called as a local operator. On the other hand, these fractional derivatives are usually non-local. Sorry. And so these derivatives are very useful while modeling memory properties in the system. Okay, so we know natural systems usually have memory. Okay, so our past always affect our present and future. So modeling such fast thing is important, and fractional derivative is one of that tool. Second thing is about delay. What is mean by delay equation? Okay, so that is in the title of this presentation, delay differential equation. So we are familiar with usual differential equation of the form dy by dx is equal to some function of y. Say dy by dx is equal to y of x. Okay, simple linear differential equation. On the right hand side, y is just function of x. So when we consider delay, then it becomes y of x minus 1 for example. Okay, so dy by dx is equal to y of x minus 1. So this is example of delay differential equation. So rate of change of this y with respect to x depends on past also. Past means here it is x minus 1. Y of x minus 1 is past value. Okay, so this is called as a delayed thing. Okay, and again such delays are useful in modeling the memory properties, past thing. Okay, so what is plan of today's lecture? So we consider the general equation of the form d alpha x of t equal to some nonlinear function g of x of t comma x of t minus tau. Here x of x is independent, x is dependent variable, and t is time variable which is independent. Okay, so left hand side is fractional derivative of order alpha of function x of t, and right hand side is a nice function of x of t as well as x of t minus tau. Here tau is constant, positive constant. So this x of t minus tau is a delay term. So basic tool here is linearization. We linearize that equation and convert it to simpler equation of this form d alpha x of t equal to a x of t plus b x of t minus tau. And then we provide the stability region. Stability region means when subset of parameter values a and b for which the system will show stable converging solutions. Okay. So these are some basic important definitions Okay, so we consider some real valued function f on positive real axis, and this is said to be in the space C suffix alpha. Alpha is a real number. If there exists a real number p greater than alpha, such that f of t can be written as t raised to p into f1 of t. Here f1 is continuous function. Then there is another space function space called C alpha m. This m is natural number as well as 0. So m can be 0, 1, 2, 3, etc. So if this mth derivative of f is in CL, okay. So this is important definition. It is called as a Riemann-Liouville integral of function. Okay. So here mu is real positive number. So integral of order mu of this function f of t, it is defined like this. So there is a kernel t minus tau raised to mu minus 1 and divided by gamma function of mu, and then this f of tau d tau. Okay. So this tau is integration variable, dummy variable. Second definition is Kaputov fractional derivative. Okay. Kaputov is name of mathematician. So here we define it like d mu f of t is equal to usual derivative of order m if this mu is equal to m, and if this mu is between two integers m minus 1 and m. Okay, so this mu is a non-integer. In that case, we define it like, first we take mth order derivative of this function f of t, and then we take integral of this quantity, integral of order m minus mu. Okay, so that this m minus mu will be between 0 and 1. Now this is our differential equation. D alpha x of t equal to some function g of x of t minus tau. This d alpha is Kaputov derivative as we discussed in this slide. Okay. We take alpha between 0 and 1. We take tau positive, and this g as a continuously differentiable function. Now, next definition is equilibrium point. What is equilibrium point? It is a solution of this differential equation which remains constant for all the time. Okay. So, we call it as x star. X star is a point. Okay, point means real number. And this is solution. This is solution means it should satisfy this differential equation. So if we substitute in equation 3, then right hand side becomes g of x of t will be x star. Okay, it is solution. X of t minus tau is also x star because this solution is constant for any time. So right hand side is g of x star x star. Left hand side is the derivative of this constant x star. And like our usual derivative, Kaputov derivative of a constant is also 0. Okay, so this is 0. So if we solve this equation g of x star equal to 0, then we get some points, the solutions of this equation, and these are nothing but equilibrium points. Now, how to linearize this equation? Okay, so we know that dealing with non-linear things is difficult. But if we consider small neighborhood, then non-linear things can be identified with linear thing locally. Okay. For example, our Earth's surface is not flat. Okay. It is like a sphere. Okay. But if we consider a small neighborhood, then we feel it like a flat. Okay. So this is subspace of Rn. That is flat means R2 plane. Okay. So even though Earth is not planar, if we consider very small region on Earth, it looks like a R2 plane. Same kind of thing is here. So this is non-linear, but if we use Taylor's formula and expand this right hand side about this point x star, then right hand side, so first few terms, say first two terms are linear. Okay. So first term will be 0 because it will be g of x star, that will be 0. So Taylor's formula. with two variables. Okay, so that term will contain partial derivatives of g with respect to first variable and second variable. Okay, and if we consider local thing, then that is sufficient for us. Of course, there are second order terms, second partial derivatives, but we can ignore those things. So locally linearized thing will look like this. Left hand side is d alpha x of t, right hand side is some constant a multiplied by x of t plus constant b multiplied by x of t minus tau. So these constants a and b are nothing but partial derivatives of this function g with respect to first and second variable respectively. And these derivatives are evaluated at this point x star x star. Now, from this we find characteristic equation. Okay, so I hope all are familiar with ordinary differential equations, and I think in second year BSc or so we find characteristic equation of differential equation. Okay, so how we find characteristic equation? Usually what we do, we replace the derivative thing. So if there is y dash, then we just put lambda. Lambda is that characteristic variable. Okay, variable in that characteristic polynomial. Okay, so if there is y double dash, we put lambda square, etc. Okay, and how we obtain these equations? There are two ways. First thing is we substitute that y equal to e raised to x, for example, or here in this format we can substitute x of t equal to e raised to t, e raised to lambda t. Okay, and then we divide that equation throughout by e raised to lambda t, and whatever we get is our required thing, that is characteristic polynomial. In this case, we are not getting polynomial because this equation is quite difficult. Okay, so another way is to use Laplace transform. Here, applying Laplace transform, we get the characteristic equation as lambda raised to alpha is equal to a plus b e raised to minus lambda tau. This exp means our usual exponential function e raised to. Okay, so this is transcendental equation. Okay, left hand side is lambda raised to alpha. This alpha is same as this derivative order, equal to a plus b raised to minus lambda tau. Now, in that case, I mean, when we deal with ordinary differential equations, about the stability of equation, okay, we know the solution is exponential form, so e raised to lambda t. So when the term e raised to lambda t goes to 0, so it is very easy thing. If our lambda is negative real number, so say e raised to minus 2t, limit as t tends to infinity, it will go to 0. And if this lambda is positive, say e raised to 5t, as t tends to infinity, it will be unbounded. Okay, so stability means solution should converge to some point. Okay, or it should not become unbounded. Okay, so these are the things. I mean, if lambda is real number, if lambda is complex number, then say if lambda is 2 plus 3i, okay, then e raised to lambda t becomes e raised to 2t into e raised to 3it. Now this e raised to 3it, this thing will be bounded because e raised to I theta is cos theta plus I sin theta, and sin cos, these are bounded things. On the other hand, that e raised to 2t, that will be unbounded. Okay, so here real part of that eigenvalue lambda play important. So if our lambda is of the form u plus iv, then e raised to lambda t becomes e raised to ut multiplied by e raised to ivt. And if this u is positive, this term will be unbounded. If this u is negative, this term will be bounded. Okay, so stability condition is like this. if real part of all the characteristic roots means roots of this characteristic equation. Usually these are called eigenvalues also. Okay, so if all the eigenvalues are with negative real part, then all the solutions will go to 0. That means this system is stable, or this equilibrium X star is stable, because whatever we are doing is in the small neighborhood of equilibrium point X. So we substitute first thing is non-delayed case. So if we take tau equal to 0, then this condition 7 takes this form, a plus b negative. Okay. So here, if tau is 0, then this thing is lambda raised to alpha equal to a plus b. And what we want real part of lambda to be negative. Okay. So equivalently, this differential equation becomes d alpha x of t equal to a plus b into x of t. And if a and b are real numbers, then the stability theory of this fractional differential equations says that this a plus b should be negative. This condition is same as our integer order derivative case also. Anyways, so this is important thing. Our a plus b should be negative. So for tau equal to 0. Now we take tau non-zero. So that means tau is positive. And we write lambda equal to u plus iv. Now, if real part is negative, then stable. If real part is positive, then it is unstable. That means what is boundary of these two regions? So boundary of these two regions is identified by real part of lambda is equal to 0. Okay. So if it is negative, then stable, positive, unstable. So boundary should be equal to 0. So what we do? We put real part of this lambda 0 means simply we put lambda equal to iv in the characteristic equation here, and we expand this. Okay, there are involved calculations, and after these computations we get equations of this form. Okay, so v raised to 2 alpha minus. Okay, so what we do? We separate real imaginary parts, square, add, and so on. Okay, so we get equation of this form, and from this we find this is quadratic in v raised to alpha. So we find v raised to alpha from this. So our aim is to eliminate this variable b. Okay, so we using 10 means using this equation, we find equation for tau. So cos inverse will be there. This ARC cos, Arc cos means cos inverse. And we substitute this v here. Finally, we arrive to these curves, and these curves are called as critical curves. So if the delay value crosses these values tau 1n or this tau 2n, then there is a possibility of change in stability. Now, even if the tau crosses these values, in general, the stability properties need not change. So when the stability properties will change? So if we find this d lambda by d tau, that means rate of change of this lambda with respect to tau. And if this is changing the sign along these curves, along any of these curves, then we can expect the change in stability. So this d lambda by d tau, after simplification, we get like this. And at u equal to 0 means along these curves, critical curves. So things are like this. So if we simplify, then we can conclude that this value du by d tau is always positive along these curves. That means we can expect at most one stability region. Okay, so this case is when the system is stable at tau equal to 0. Okay, then we get stability at that point, and this du by d tau is positive, so nearby critical curve. Okay, so stability region will be bounded by origin and that nearby such curve. Curve means this one, whatever the smallest value, and that smallest value is at n equal to 0. So that will be tau 1 of 0. Okay, so these are some observations. First observation, if this a plus b is negative, then at delay tau equal to 0, we get stable solutions. And from these equations 15 and 16, this one is 15 and 16, there is some square root thing, raised 1 upon alpha, etc. So we don't want these things to be negative. Okay, otherwise we get complex value, and this delay is not complex number, it is a real positive. So we assume this b square is greater than a square sine square alpha pi by 2. And second thing, we assume a cos alpha pi by 2 plus this square root thing, b square minus a square sine square alpha pi by 2 is positive. Okay. So we have all these conditions. The stability region is then bounded by the plane tau equal to 0. Why I'm saying plane tau equal to 0? Because we are in 3-dimension thing. Okay, this space is a, b, and tau, 3 variables. Okay, so this tau equal to 0 defines a plane in this space, and the closest critical curve tau 1 of 0. If one of the conditions 21 and 22 is not satisfied, then the stability properties will not change in this region a plus b negative. That is, the solutions are stable for any tau greater equal to 0. Okay, so if solutions are stable at tau equal to 0, and if these conditions are violated, then we will not get any critical curve. Means whatever stability is at tau equal to 0, it will remain for all the delay values tau positive. If a plus b is positive, then system is unstable at tau equal to 0. Okay, and it will remain unstable for any tau greater equal to 0. So these are further observation. Change in stability of equilibrium can occur only if the conditions 21 and 22 are satisfied along with a plus b negative. Okay, 21, 22, I am again showing these are the two conditions. These conditions are equivalent. Okay, so if we combine these two conditions, we get a simpler looking condition. That is, b belongs to minus infinity to minus mod a. And if b is not in this interval, then we have following two cases where the stability properties do not change for any tau greater equal to 0. So first thing is, if b is between, okay, b is not in this interval means it is in minus a to infinity, then a plus b is positive and we get unstable solutions. This is first case. Second case is b is between a to minus a. Okay, note that here a is negative. So this a is a negative number, this minus a is positive. Okay, so b is in this open interval, then a plus b is negative, and hence the solutions are stable for any delay value. This is the theorem. Suppose a star is an equilibrium solution of the generalized delay differential equation d alpha x of t equal to g of x of t minus tau. Here 0 less than alpha less equal 1, fractional order, and a, b are partial derivatives of g evaluated at x star. So case 1, if b belongs to this minus infinity to minus a, then the stability region of this equilibrium point in the tau AB parameter space, okay, these are the 3 variables, is located between the plane tau equal to 0 and the curve or surface, we can say. Tau AB alpha equal to cos inverse of this. Okay, it looks quite complicated. The equation undergoes bifurcation. Bifurcation, I will explain what is meant by bifurcation. If b is between minus a to infinity, then this equilibrium point is unstable for any tau greater equal 0. If b is between a to minus a and a is negative, then equilibrium point is stable for tau greater equal 0. The curve tau AB alpha given by equation 24 is called boundary curve. Okay, so this we call this curve as boundary curve. So this can be viewed pictorially. Okay, now things were looking quite difficult, but this theorem can be summarized like this. So what we have to do? What we have? We have a differential equation d alpha x of t equal to some function g of x of t comma x of t minus tau. Okay, so first step is to find equilibrium points. So how to find equilibrium points? We have to solve the equation g of x star comma x star equal to 0, and the solutions x star of this equation are equilibrium. This is first step. Second step is to find partial derivatives of function g, okay, with respect to first and second variable. Evaluate these derivatives as at point x star, and then call these derivatives as a and b, and this is AB plane. Okay, this curve is a equal to b, and this curve is a equal to minus. So if our parameter values a and b, okay, so if the partial derivative values are here in this green colored region, then we can directly say that the solution will be unbounded. This u means unstable. If the values a and b are here in the yellow region, then we can directly say that the solution will converge to 0 as t tends to infinity. And third thing is this brown colored region. Here things depend on delay. So we will find one value of delay, that is this one. We will call it as tau star. Okay, we have alpha a and b. We substitute here, and then we get a number. Okay, we call it as tau star, critical value of tau. And here in this brown region, the things are like this. If our delay value is between 0 and tau star, then we get stable solution. And if we cross that value, tau star, then we get unstable. Okay, so this is important region ds. Let me consider some example, then I will be back to this theory. Okay, so this is a simple linear rational order delay differential equation. Okay, d alpha x of t equal to minus 3x of t plus 24 sin x of t minus tau. Okay, sorry, it is not linear, it is non-linear. Okay, due to this sine function. Here g function is this right hand side. This x suffix tau means this x of t minus tau. Okay, and if we solve this g of x star equal to 0, then we get so many solutions. These are 0, plus or minus 2.78, plus or minus 7.49, plus or minus 7.95. Okay, so 2 plus 2 4 plus 2 6 7. There are 7 equilibrium points. Okay, and for each equilibrium point we can have small a and small b. Okay, so if we consider this 0 origin, 0 point, then if we substitute this 0 in the partial derivatives, okay, here a is always minus 3 because partial derivative with respect to x is minus 3, and partial derivative with respect to this x of t minus tau is 24. Derivative of sine is cos, so 24 cos of x of t minus tau. So we need to substitute this value 0 in cos. So cos 0 is 1, so b is 20. Okay, like this we have to find all these values, and then we have to come back to that figure here. So minus 3 and 24, where it is. So our a is minus 3 means it is negative, and b is 24, so we are in this region green. So we can directly say that the solutions will be unstable if the initial condition is in the neighborhood of that equilibrium point, that is 0. Okay, so this equilibrium point is said to be unstable. Okay, means if our initial condition for this differential equation is very close to this x0, then solutions will go away from this x0. That means unstable. Okay. Now I am moving to second part of this lecture, that is bifurcation thing. What is meant by bifurcation? Bifurcation means change in the stability properties. Okay. So we have parameters, means constant values a, b, and tau. So what is mean by bifurcation occurs? Bifurcation occurs at some value of parameter, say a equal to 3 is bifurcation value. Means if I am taking value of a less than 3, say a equal to 2.8, 2.9, etc., then I will get one property, say stable solution. And if I am crossing that value 3, say if my a is 3.1, 3.2, etc., then I will get unstable solutions. Okay, so bifurcation occurs means stability properties will change. Okay, so here we provide more details of this region ds. Okay, so this is now new work. So we consider these regions in this figure. First region is U, that is unstable region when a plus b is greater than 0. Okay, here a plus b is greater than 0. Second region is S, if a is negative and a is less than b is less than minus a. Then we are here, we get all the stable solutions for any delay value, for any fractional order alpha between 0 and 1. And third, fourth, and fifth are new regions. Okay, so I should refer to this figure. Okay, so this ds region is divided now in 3 regions. This is ds1, this is ds2, pink color, and this is ds3. So here in ds1 region, we get stable region in alpha tau plane as shown in figure 3. So figure 3 is like this. Okay, so if we are in the region ds1, things will look like this. Means for higher values of fractional order alpha, we get stable solution, and if we decrease fractional order, then somewhere we get unstable solution. Okay, so this region is called as ds1. If our parameter values are here, if our parameter values are in this pink region, then we get the region ds2, and ds2 will look like this. Okay, so for higher values again we get stable, for lower values of alpha we get unstable. Along with there is one more thing. So if we cross some delay value, so for higher values of delay, it is unstable for alpha near 1. In between it becomes stable, and again it becomes unstable. So this is second region, ds2. And there is ds3 region, which is exactly opposite of ds1. Means for higher values of fractional order, we get unstable solutions, and for if we keep on decreasing fractional order, then we get stable solution for smaller values. I'm explaining all these regions. How much time I have? Coordinator, chairperson. Are you there?
Yes, sir.
किती वेळ आहे अजून? किती वेळ आहे अजून माझ्याकडे?
एक 5 मिनिटाचा आहे कालावधी सर.
ठीक, मी थोडं समराइज. ओके. So I think I should go to examples now, because I don't have sufficient time to prove these things or explain these regions. Okay, so basically this figure is important. Okay, so this figure was important in earlier things. Now when we are here, we are providing bifurcations, 3 different types of things. Okay, so these curves are well defined, given by formulas. Okay, so such formulas are there. These formulas look complicated, but These are very common things in the research, mathematical research. Okay. We don't have any option. So I should go to examples. So this I was discussing. So for this first equilibrium x0, we are getting unstable thing. Next, these two equilibrium points x1, 2. For both these things, my a is -3. It will always be -3, and b is -22.49. So here we can observe that our b is between -infinity to minus mod a. So stability region is located between tau equal to 0 and tau n equal to 0. So this is delay dependent thing. Then for x34, our a is -3, b is 8.369. Okay, it can be calculated. It is cosine of that value. Okay, cosine of this 7.49. So b is between -a to infinity, and equilibrium points are unstable here. And the last case is for x56, I think. X56, here a and b are like this, and here equilibrium points are stable for any value of delay. We can verify these results by solving these equations. And if we solve these equations, we get the required things. Okay, so for first case, we are getting stable solutions. Okay, here we are getting, these are called as limit cycles, so oscillating solutions. Okay. So it is converging to closed orbit. Okay, this is closed orbit. Here in the unstable region, we are getting chaotic solutions also. This is for fractional order 0.8 and delay value 0.1. Okay, so this is oscillations are there, but not periodic oscillations. So okay, system always keeps oscillating, but oscillations are not periodic. And if we sketch this in the plane, horizontal is x of t, vertical is x of t minus tau, then we get such attractive figure. This is called as chaotic attractor. This is for alpha equal to 0.8 and delay value tau equal to 0.15. We are getting stable solution for this value, alpha 0.6, tau 0.3, and so on. This is second example where nonlinear terms are quadratic and cubic. And equilibrium point is 0. Okay, if we put x equal to 0, this equation is satisfied. And at 0, our a is -9, b is -10.9. So for this a, okay, our earlier case, there are two things, a0 and a1. So -11, and this is around -11, and a1 is -10. So we are in the region DS2. Okay, and so the stable region is as shown in figure 4. This one, figure 4. Okay, so we are getting different stability properties. So we get these two critical values for tau. So if we fix tau equal to 0.38, which is less than tau star, then we get critical value alpha 0.38. So we get stable solutions for this fractional order smaller than fractional order bigger than this 0.38. That is for alpha equal to 0.45, we get stable thing. Unstable for smaller than this, say 0.3. Okay, so this is stable solution. This is unstable solution, and so on. Okay. So similar analysis can be done for other examples. I know it is insufficient time to explain the things. I'm sharing the title of the paper, so those who are interested, they can go to that paper and see. So I'm sharing that slide again. Okay, so these are the two main papers from which it is discussed. Now it is published papers. Its preprint is available on archive, so it can be downloaded. So thank you very much. If there are questions from audience, they can ask. काही प्रश्न असतील तर विचारू शकता. I think there is no any question from audience. Session can conclude.
Hello. Good afternoon, sir. And good
Thank you, sir.
afternoon to all the participants. First of all, I am very much thankful, sir, for giving a nice lecture in simple and lucid way on analysis of fractional order delay differential equations. Now, in the first part, you have explained the basic definition or described the basic definitions related to fractional order delay differential equations. Then what are the stability conditions for the fractional order delay differential equations? Then afterwards, in very simple way, compute fractional derivative of function f. Then what is the generalization of delay differential equation and how to obtain its solution? Further, stability conditions of fractional order delay differential equations, expression for crucial curve, stable and unstable solutions, or conditions for stable and unstable solutions. Then the change in the stability of equilibrium, and one nice theorem which is related to equilibrium solution of generalized delay differential equations. And finally, sir, you have explained bifurcation regions in a very simple way by the help of graph. So I am very much thankful to you on the behalf of DP Bhosle College, Koregaon. Also, I am very much thankful to the organizing committee of DP Bhosle College, Koregaon, particularly Ashwini Salunke madam. Thank you. Thank you very much, sir.
Thank you, sir.
Now over to organizing committee.
Thank you, both of you. Now our session is over. We meet after 20 minutes for session 3. Thank you, all. All participants has requested that join after 30 p.m. Thank you. Sorry, 3 p.m. Good afternoon, all of you. Please everybody join. I welcome you for the session 3. I request to Ms. A.K. Chinke to introduce our chief guest and our chairperson. Over to Ashwini Chinke.
Good afternoon, all of you. It gives me immense pleasure to introduce and welcome today's resource person, Honorable Dr. V.B. Gutte, sir. Dr. V.B. Gutte, sir, is working as a professor and director, School of Computational Sciences and Head of Department of Statistics, Punyashlok Ahilya Devi Holkar, Solapur University, Solapur. He is completed MSc and PhD. Sir is having 33 years teaching experience as a UG and PG level. He is act as a registrar, director, School of Computational Sciences, in charge director, School of Allied Health Sciences, head of Department of Mathematics and Statistics, director, Knowledge Resource Center, KRC Library. He published 40 research in national and international journals. He presented 80 research papers in national and international conferences. Sir invited as a resource person in 35 conferences and workshops. He organized 10 conferences, seminars, workshops, and 15 chaired sessions in conferences, seminar, and 10 guest lecture as a colleges and university. He awarded as an International Academic Excellence Award by International Institute of Organized Research, India. Sarvapalli Radhakrishnan Best Teacher Award by Shikshak Kalyan Foundation, New Delhi. Best Teacher Award by PAH Solapur University, Solapur in August 2021. Best Performance in the Department of the Statistics by Hindustan Unilever Limited in November 2017. Also, Best Teacher Award by Lions Club of Solapur, CASI Community Leader Award by Maha Walkathon 2018, Mumbai. Sir work as a member of Senate, Management Council, Academic Council at PAH Solapur University, Solapur. Member of Governing Body, Member of Academic Council, also Member of Research and Recognized Committee at Mumbai University, Mumbai. PAH Solapur University, Solapur and Shivaji University, Kolhapur. He worked as a chairman, head of Board of Studies in Statistics, member of Board of Studies in Statistics and Computer Applications at Savitribai Phule, Pune University, Pune. Member of Board of Studies in Statistics, member of Board of Studies in Business Eco, Banking, Mathematics and Statistics at Shivaji University. Member of Board of Studies in Business Statistics and Business Mathematics at the DG College, Satara. Member of Board of Studies in Statistics of various autonomous colleges and also university representative. Today we have such a well-known personality in statistics with us, Dr. V.B. Gutte. It's our proud privilege to have him as a resource person. I request to Dr. S.R. Supnekar, Head of Department of Statistics, Balasaheb Desai College, Paltan, to chair this session. Now I request to Dr. Gutte sir to start the invited speaker.
Good afternoon to all. May I audible? Supnekar sir. Hello.
Yes, sir, you are audible.
Yes. Okay. First of all, I wish to thank Honorable Principal Dr. V.S. Sawant sir of DP Bhosle College, Koregaon, Head Department of Mathematics, Salunke Madam, entire organizing committee of this National Conference on Recent Trends in Mathematics and Statistics for inviting me as a resource person for this conference. Earlier, I was the part of Rayat Shikshan Sanstha family. I have worked 20 years in Rayat Shikshan Sanstha's Karmavir Bhaurav Patil Mahavidyalaya, Pandharpur, and then I have shifted to Punyashlok Ahilyadevi Holkar Solapur University, Solapur. So thank you once again for giving me this opportunity for sharing my research with you. The topic that I have selected for presentation is monitoring mean and variability by auxiliary information based control charts using runs rules. So control charts, all of us know, that is, control charts are widely used in industry. It is an industrial tool, and its use is to see whether any production process is in control or out of control. If the process is in control, then we say that there is no problem in production. But if process is out of control or process goes out of control, then problem in production occurs. That means instead of regular atoms, some defective atoms may be produced in the process. So defective atoms, if occurs in the process, then it is a loss of producer, in the sense that whatever raw material used for that production, then the labor charges and other expenses, so totally it will be loss of the producer. So statistical process control tool as a control chart, it is widely used in industry to see whether the process is in control. That means the production is in the standard form. Whatever standards we have provided for the machine, whether the production occurs as per that standards. So it is the main purpose of using control charts. Now control charts are generally used for monitoring process mean as well as process standard deviation. Process mean chart, generally we use X bar chart for monitoring process mean, and Shewhart S square chart, it is used for monitoring process variance. Now, as these are the Shewhart type control charts, these control charts are applicable in the industrial process to detect the shift of large size. That means if there is a large change in the process mean or in the process variance, then only Shewhart type charts are applicable. So for detecting small shifts in process parameters, these charts are not suitable. So what is alternative for this? So in literature, some other control charts are developed as an alternative for detecting small shifts in process parameters. And these charts are Kusum chart, that's cumulative sum chart, exponentially weighted moving average chart, and moving average chart. So these are the alternatives for Shewhart control chart. Now in literature of quality control, there are many strategies are used to improve the performance of control chart. So use of run rules, auxiliary information, or use of double sampling, such strategies are always used in literature to improve the performance of control chart. So to improve performance means we have to develop a control chart, or we have to design a control chart such that it can detect the change in process parameter as early as possible. So use of auxiliary information based control chart, it is a one strategy that is used to improve the performance. So auxiliary information means in traditional control chart, X bar or R chart or a square chart, we generally use the one quality characteristic X and we take the measurement on that quality characteristic. For example, from these measurements, we can calculate sample mean, we can calculate sample standard deviation, and we use these statistics to construct control charts for mean or control charts for variable. Now, in auxiliary information, along with the quality characteristic X, we use one more quality characteristics, and that quality characteristic we call it as the auxiliary information. And in statistics, we know if we have a more and more information, then we may accurately or correctly predict the values. So here, along with study variable, we use one more auxiliary variable. That means we have some more information about that quality characteristics. And so if we use such auxiliary information in the construction of control chart, definitely such control charts will be more efficient than the traditional control chart. For example, if we consider the refill machine, refill of bottles, then quantity that contained in the bottle is our study variable. Quantity contained in that bottle is our study variable, which is to be monitored by using the control charts. Along with that filling of bottle, if we consider one more variable, that is suppose time of filling. So time of filling is the additional information. Actually, filling quantity is study variable, and time of filling, it is the additional variable, and we use these two type of variables in the construction of control charts, and such control charts we call it as the auxiliary information based control charts. In literature, many auxiliary information control charts are developed for monitoring process mean, process variable. But again, in literature, there is a search for further improving the performance of these auxiliary information based control charts. That means first traditional control charts, that are Shewhart type control charts. Improvement in that Shewhart type control chart is auxiliary information based control chart. And next, we have to improve the performance of these auxiliary information based control chart. So here, these are some researchers who have developed the auxiliary information based control chart. For example, Riaz 2008, Riaz 2008B, Riaz and Doze. These authors have developed the auxiliary information based control charts as an alternative to Shewhart control charts. So these are the review of literature. Now, along with this auxiliary information control chart, some authors combined these auxiliary information based control charts with some other scheme. Some other schemes are like this: use of adaptive sample size, use of double sampling, use of synthetic control chart, or use of run rules for further improvement in the AIB control charts. So these authors are Ahmad in 2013 developed auxiliary information based variable control chart under double sampling scheme. Huck and Co, they have used synthetic control chart. Arshad, he has developed auxiliary information based EWMA chart or synthetic EWMA control chart. Now, use of run rules. It is a one strategy that is used in the literature for improving the control charts. And many authors have worked on these run rules. For example, these authors are Champ and Udall, Kelly, Ho, and Zhang and Wu. So these authors have developed the control charts based on run rules to monitor or to improve the performance of traditional control charts. Now, in this talk, we have to combine two things. First thing is auxiliary information based control chart, and then we apply simultaneously runs rules technique to this AIB chart. So this will improve the performance of auxiliary information based control chart. So auxiliary information based control chart, these are already shown as the better than Shewhart control chart. Further, we improve the performance of this AIB chart by using the runs rule. So this is the main object of this presentation. Now, as we have seen, auxiliary information means it contains two variables. One variable is study variable and other variable is auxiliary variable. So for construction of auxiliary information based control charts, we require a bivariate data. So here we consider the pair yi, xi. What is yi? Yi is the variable under study, which is to be monitored. What is xi? Xi is the auxiliary variable that is correlated with the study variable. And this bivariate random sample we consider from the bivariate normal distribution with the parameters mu x, mu y, sigma y square, sigma x square, and correlation coefficient rho. Now, based on this bivariate sample from bivariate normal distribution, we define the statistic x bar, y bar, that is called sample means of study variable and auxiliary variable. Sy square and Sx square, these are the sample variances of study variable and auxiliary variable. And based on this information, we use the unbiased regression estimator of population mean mu y. So here the mean to be monitored is mu y, and therefore we construct the regression based estimator for monitoring the process mean by using the auxiliary information, and that statistic is given by equation number 1. Simply for constructing X bar chart, we require sample means only. So here to construct auxiliary information based mean chart, so that statistic is M, and this statistic requires Y bar, that is sample mean of study variable, X bar sample mean of auxiliary variable, mu x, that is mean of auxiliary variable, and this is the regression of y on x, regression coefficient. So this is the statistic which we want to construct on the control chart instead of X bar chart. For X bar chart, which value we plotted on the chart? We just plotted X bar values against the 3 sigma control limits. So instead of that X bar, this is our charting statistic, and we plot these values on the chart. So, and also we know control charts requires the 3 sigma control limits. So these control limits for the chart are given. Second statistic that we want to construct is the variability chart. In traditional way, Shewhart R chart or S chart, these are used to monitor process variability. But here we use the regression estimator, which is based on auxiliary information, that is statistic E, and we calculate this statistic for the bivariate random sample, and we plot this statistic on the control chart with 3 sigma control limits, and plot all these V values on the chart. If all sample point lies in the control limits, then we say that the process is in control. If any of the point lies outside the control limit, then we say that process is out of control. So this statistic is used for monitoring the process variability. Now, these are the auxiliary information based control chart. And in auxiliary information based control chart or Shewhart control chart, the process goes out of control if any single point goes outside the control limits. Outside the control limits means if the plotted point lies above upper control limit or below lower control limit, then that process is called out of control. But if we use run rules technique, then run rules technique directly does not use out of control based on single plotted point out of control. So there are run rule scheme which we apply to auxiliary information based AM chart and auxiliary information based B chart. Here we use two types of rules. First rule is 2 of 2 scheme. That means when two consecutive points, plotted points, goes outside the control limit, then we say that the process is out of control. Otherwise, the process is in control. Second run rule that we are going to use for auxiliary information charts is 2 out of 3 scheme. So in this scheme, when we say process is out of control, so if we plot 3 points on the control chart, and out of these 3 points, if 2 points are plotted out of control, then and then only we say that the process is in control. So what is difference between traditional control chart and this control chart? The difference is that traditional control chart gives out of control process as early as possible. Single point plots outside the control limit. And here only 2 points goes out of control Okay. Sorry for inconvenience. There was some technical problem. Now, may I audible? आवाज येतो का आता? आवाज येतो का? हॅलो.
Yes, sir.
हाँ. So we now use runs rules for improving the performance of auxiliary information based control chart, and these run rules are two of two scheme. That means 2 points, consecutively 2 points plots outside the UCL or above UCL or below LCL, then we say that the process is out of control. Second run rule is 2 out of 3 scheme. In this scheme, if we plot 3 points on the control chart, and out of these 3 points, if 2 points lies outside the control limits, then we say that the process is out of control. So this run rule scheme is different from traditional control chart. In traditional control chart, what we do, if single point goes out of control, then we say that the process is in control. But in run rule scheme, in first rule, 2 points, both points goes out of control, then only the process is out of control. And in next scheme, 2 out of 3 points goes outside the limits, then the process is out of control. So we apply these run rules for the above 2 control charts. Now, in order to measure, once we apply the run rules to control chart, how to decide which chart is superior or efficient? So for that purpose, we use the performance measure of the control chart, and that measure is called the average run length. In short, it is called ARL. So the number of points to be plotted on the control charts for detecting first out of control, it is called ARL. Now there are 2 types of ARL. First one is in control ARL, which is denoted by ARL 0, and second is out of control ARL, which is denoted by ARL 1. So these 2 ARLs are used as the performance measure of the control chart. So which control chart is superior, which control chart is efficient, it can be decided based on this ARL. So to measure the performance of control chart, we use bivariate random sample from normal distribution, and we have to monitor the study variable y. In first case, we have to monitor mean of this study variable. So that means we have to give the shift of size delta in the mean of study variable y, and that shift is denoted by delta. When delta equal to 0, then we say that there is no shift in the process mean. If delta is not equal to 0, then we say that the process mean is shifted. And once the process mean is shifted, then it is expected that our control chart should detect that shift as early as possible. So for in control process, we take a random sample from bivariate normal distribution with mean 0, 0, variances 1, 1, and correlation coefficient between study and auxiliary variable is. And for out of control process or shifted process, we just shift the mean of study variable y from 0 to delta. Other parameters are same, only the mean of study variable y is shifted by delta, and this is in control process 0, 0, 1, 1 row. It is in control process, and this is the shifted process. Now, from this, we have to study how our control chart detect the shift in process mean as early as possible. So for that purpose, we take different values, sample size, subgroup sample size, for example, n equal to 10, n equal to 15, n equal to 20. In control ARL is generally fixed as 200. Correlation between study variable and auxiliary variables, we have taken 3 values. For no correlation effect, we take 0.4, rho equal to 0.4. For moderate correlation effect, we take rho equal to 0.7 and 0.9 for high correlation between study variable and auxiliary variable. And we present the ARL values of the control charts here. Now here, first column of this table, it is nothing but the shift in process parameter. This is shift in process parameter. So if delta equal to 0, that means there is no shift in process parameter. So when there is no shift, that means our process is in control, and in control ARL for all the situations is taken as approximately 200. Approximately 200. Then second part of the table, it is for rho equal to 0.4. When the correlation between study variable and auxiliary variable is 0.4, then 0.7 and 0.4. Here, this is traditional control chart, that is Shewhart's control chart. This is 1-of-1 control chart. That means our traditional control chart. One plotted point lies outside the control limit, then we say that the process is in control. So this is called 1-of-1 chart. Second, 2-of-2 chart means if 2 plotted point goes out of control, then that chart is called 2-of-2. And 2-of-3 chart, it means out of 3 plotted points, if 2 points lies outside the control, then it is called 2-of-3 control chart. So for different charts and different correlation levels, we will see the out of control ARL values. This is for correlation 0.4, for correlation 0.7, and this part is for correlation 0.9. And here subgroup sample size n is taken as 10. Now see here, if we use traditional X bar chart, if there is a shift of 0.1 in the process mean, when the process mean shifted from 0 to 0.1, then this Y bar chart requires 137 samples to be plotted on the chart to detect this shift. The process out of control गेली हे डिटेक्ट करण्यासाठी आपल्याला किती सॅम्पल्स लागतात 137, which is quite large. हेच जर आपण 1-of-1 रूल वापरला ऑक्झिलरी इन्फॉर्मेशन बेस्ड 132 सॅम्पल लागतात. 2-of-2 वापरला 131 सॅम्पल it will require, and 2-of-3 it will require only 124 samples. That means this 2-of-3 run rule detect shift of size 0.4 earlier than the Shewhart type chart or 1-of-2, 2-of-2 chart for low level of autocorrelation. Now what happens if we change the level of autocorrelation as rho is equal to 0.7? That means correlation between study variable and auxiliary variable is 0.7. So here these ARL values are smaller than the rho equal to 0.2. So the correlation, if the correlation increases, what happens? The ARL value decreases. And for rho equal to 0.9, again these value decreases to 54, 49, 45. So in all these cases, the auxiliary information based control chart for 2 of 2 run rules, it require only 49 samples to be plotted on the chart to detect shift of point. 2 of 3 rules requires 45 samples on the chart to detect this shift. 1 of 1 rule requires 54 samples on the chart, and traditional X bar chart requires 157 samples. So one thing is clear, that auxiliary information charts are having smaller out of control area. That means auxiliary information based control chart detect shift in process mean as early as possible. Again, for these auxiliary information based control charts, if we use run rules, then that run rule scheme again detects shift earlier than without run rule. See here, 1 of 1 is without run rule. It requires 54 samples. 2 of 2, 49 samples, and 2 of 3, 45 samples. So these two require small samples to detect this shift. Hence, the run rules chart perform better than the without run rules chart. So this is the important characteristics of the run rules. Now next table we have performed for subgroup sample of size n equal to 15, and as sample size goes on increasing, the performance of run rule chart again improves. That means in this chart, here we require 45 samples to be plotted for n equal to 10. But here, for n equal to 15, to detect shift of size 0.1, we require only 27 samples. That is minimum samples. Or in other words, we can detect this shift as early as possible. And again, if we increase again this sample size to 20, see here, n equal to 20, for detecting shift of size 0.1, it requires only 18 samples. So in this way, if the out of control ARL becomes smaller, means our control chart perform better. ARL smaller means that control chart detects shift faster, and therefore it is efficient. So this is about the control chart for monitoring the process mean. In the same way, we have developed the run rules control chart for monitoring process variability, and these process variability charts are given here. S square chart, it is the Shewhart type chart. We use it as the reference chart or competitor for auxiliary information based chart. And here again we take 3 sample size, n equal to 10, n equal to 15, and n equal to 20. In control ARL is 200. So for variability, in control variability means the process parameter lambda is 1. So for in control process parameter, all the control charts have approximately same in control ARL value, and we compare this situation now only for out of control situation. So first column is the shift in process variance. So shift in process variance of size 1 means process variance has not changed. There is no change in process variance. So it is the in control situation. Here process variance change 1 to 1.1. Here 1.2, 1.3, 1.4, 1.5. So variance of the process changes. And effect of this variance is detected by S square chart. For example, detecting this shift, a square chart requires 47 samples. Our auxiliary information chart requires for no correlation 46 samples. That means these are approximately same. But if we use 2 of 2 run rules, it requires only 38 samples. If we use 2 of 3 rules for this chart, then it gives 36 samples. That means out of control ARL requires smaller if we use the run rules. Similarly, as the level of correlation increases, that means the correlation between study variable goes to 0.6, moderate correlation, then this out of control value decreases. So 42, here 46 1 of 1, it becomes 40. Here 2 of 2, 38, it becomes 35. Here 2 of 3, 36, so it becomes 31. And same values again reduced for higher correlation between study variable, that is rho equal to 0.9. So this out of control ARL value becomes again smaller, and hence we say that our auxiliary information based V chart perform better than with run rules, perform better than without run rules. So this is the table for subgroup sample size n equal to 10. This is the table for subgroup sample size n equal to 15 for V chart. So again here, as sample size increased, that means we have gathered more information. So out of control ARL values are reduced. That means the chart perform better. And similarly for n equal to 20, again this ARL value reduces. So the performance of the chart goes on improving as the sample size increases, as well as the level of correlation between study variable and that variable increases. So these are the observations what we have seen in the tables. Now again we have considered 2 examples. This is for mean chart and this is for variability chart, and we have plotted this chart here. This is upper control limit 1 of 1 and 2 of 2 chart. So 1 of 1 chart goes out of control at this point number 15, that means later. But run rules chart detect first out of control here. So these 2 of 2 chart detect shift in process mean earlier than this point. So this is the advantages. Similarly, we have this is variability chart. In this variability chart also, for 2 of 2 run rules, this point goes outside the upper control limit. That means 2 of 2 chart detects shift here, and 1 of 1 chart detects shift here, which is later and this is earlier. So this is the advantage of run rules. That means run rules chart detect shift in process parameter earlier than the chart without run rules. So these are the conclusions, and these are some references which are used for preparation of this talk. If you have any questions, then you can ask. Any questions, discussion, please? Supnekar sir.
Hello, Supnekar sir.
काय पण केलं तुम्ही रेकॉर्डिंग होणार स्क्रीनशॉट काढ.
Hello, Supnekar sir.
Okay. Hello, sir. I am audible.
Yes, yes, sir.
हा मला मगाच्यानं अनम्यूटच केलं नसल्यामुळे बोलता येत नव्हतं.
Okay.
Good evening to all the dignitaries and participants of this session. I am Dr. Sanjay Supnekar from Balasaheb Desai College, Patan, and it is my great pleasure to chair this session. So, Honorable Professor Dr. Gute sir given a nice information, and it is very thoughtful lecture on the topic monitoring mean and variability by auxiliary information based on control charts. Actually, Professor Gute is the master of this control charts. So he has introduced some new techniques to develop the control charts. He has alternative charts for small process shifts. Actually, it is the Sieverts type AIBM and AIBV charts with run rules techniques he has used, and their performance evaluation and comparison is given by the based on ARL. He also studied the simulation study. The conclusion is the auxiliary information based control charts requires very small sample size, and therefore we earlier invest actually the out of control. So it is a very nice lecture, sir, you are given. We are grateful for the time and effort you took to share your thoughts and experience with us. Sir, your research, your depth of understanding of users' interfaces, and your ability to present the topic in such an interesting way produced such an interesting way of producing of the most memorable evening in this conference. I personally appreciate your approach to anticipating participants' intent. So it is a great session, sir. So I am very thankful to you, and also I am thankful to coordinator and Salunke madam to give me such an opportunity. So thanks to all, and over to the coordinator.
Thank you, sir. Now the next session is the paper presentation. Dr. Sajne madam, please join this session.
Hello everyone. For presentation of statistics subject, please join Google Meet link, share in group. Please join Google Meet link.
मॅडम आवाज येतोय?
हॅलो हॅलो
मॅडम आवाज येतोय?
हॅलो येतोय?
हा येतोय येतोय, तुमचा येतोय.
हा, पहिल्यांदा मी ऑर्गनायझरचा आभार मानते मला ही अपॉर्च्युनिटी दिल्याबद्दल. आणि आता या सेशनला आपण सुरुवात करूया.
Oh, madam. 13 participants are participated in this paper presentation. I will call you the presentation for More Gauri Narayan. Use the chat box for the remark. More Gauri Narayan.
प्रेझेंटेशन आहे, सेशन सुरू झालंय, सगळ्यांनी जॉईन केलं आणि चॅट बॉक्स मध्ये
पेपर presentation. शिंदे दत्तात्रय निंबाजीराव. In the session.
पेपर प्रेझेंटेशन
Hello. Hello. आता पुढचं कोण आहे का नाही? गौरी मोरे मॅडम. स्क्रीन होय हो. Hello, Shinde sir. Hello, may I audible, Shinde sir? Hello, please unmute yourself, Shinde sir. Shinde sir, your screen is visible, but you are not audible. Please unmute yourself. Hello, Dattatreya Shinde sir. May I audible? Please use chat box if any problem is there. Hello. Next. Hello. Hello. Gauri More madam, are you audible? Hello, Shinde sir. Shinde sir. Hello. Shinde sir, unmute yourself. We have unmuted you, sir. काय करू? कसं घ्या? Hello, Shinde sir, wait, please wait. Gauri madam, Gauri More madam, are you present here? Use chat box. All the paper presenters, you have to use chat box that what name you have used in this Google Zoom meeting link, because we are unable to guess that what is your name in the present Zoom meeting.
पुढच्या पार्टिसिपंटना तोपर्यंत सांगा मग.
Gauri More madam, are you present?
Yes, sir. Am I audible, sir?
Yes. No problem.
Okay.
You can start. Please, all the paper presenters, you have to complete within 4 to 5 minutes because there are 13 to 14 paper presenters and we are having less time. We have already covered 4 PM now.
Okay. Can I share my screen, sir?
Yes, ma'am.
Is it my screen is visible, sir?
Yes, visible. Okay.
Okay. Thank you, ma'am. Good evening, all. I am Gauri More from Department of Mathematics, Yashwantrao Chauhan Institute of Science, Karmavir Bhaurao Patil University, Satara. In this paper, I am here to present our research work entitled with on existence, uniqueness, and stability result for a nonlinear mixed fractional integral differential equations in Banach spaces with non-local boundary conditions. The main objective of this paper is to investigate the existence, uniqueness, and Ulam stability of solutions of mixed fractional integral differential equations involving the capital fractional derivative. We use the well-known Banach contraction principle and Schaeffer's fixed point theorem to prove our main results. And at the end, we give one example to illustrate the obtained results. In this paper, we work on the problems defined by equation 1 and 2. Capital fractional derivative of order alpha y of t equal to xi y of t plus f of t y of t integration from 0 to t k of s y of s ds integration from 0 to t h of s y of s ds, where t belongs to closed interval 0 to t and alpha lies between 0 to 1 where xi is strictly greater than 0 with the non-local conditions y of 0 equal to y0 plus g of y. Here f, k, h and g are continuous functions. These are some preliminaries which we have used to prove our results. Some theorems, Banach fixed point theorem, Schaeffer's fixed point theorem, Parts-Patte inequality, etc. The lemma 0.3 is about y of t is the solution of the, or y of t satisfies the given problem if and only if y satisfies this integral equation. So we use this lemma in our further discussion. These are some hypotheses which we have used in this paper. Now we are moving towards the main result of our paper. Theorem 3 is about the uniqueness of solution of the given problem. So if the hypothesis H1, H2, H3 are hold, and if the value of delta represented by equation number 4 is strictly less than 1, then the given problem has a unique solution where the value of m and n are defined here. So to prove this result, hello sir.
Yes, sir.
Hello. Hello sir. Am I audible, sir?
Yes, yes. Yes, ma'am.
Okay. So to prove this result, we use here the Banach fixed point theorem. So for that, we define one operator T from C of JR, that is space of all continuous functions from J to R to C of JR. And we define that operator as represented by equation number 5. So we consider the 2 points x of t, y of t belongs to C of JR. And for all t belongs to J, we obtain this term, that is norm of tx of t minus ty of t. So substituting all the value and further simplifications, we obtain that norm of tx minus ty is less than or equal to delta norm of x minus y. But from equation 4, we observe that the value of delta is strictly less than 1. So we conclude that the operator T is a contraction map. So by Banach fixed point theorem, the operator T has a unique fixed point, and that unique fixed point is the unique solution of the given problem. Now the theorem 4 is about the existence of the solution. So if the hypothesis H1 to H4 are hold, then the given problem has at least one solution. So the proof of this theorem contains 4 steps. So in step number 1, we show that the operator T, which is defined in last theorem, is a continuous. So we use here the sequential criteria of continuity. So for that, we consider one sequence xn in the space of all continuous functions from J to R, where that sequence converges to x in C of JR. So now we consider norm of txn of t minus tx of t. So by putting this value, observe that as xn tending to x, this norm of txn minus tx tends to 0 as n tending to infinity. Now in the step 2, we show that the map T maps bounded sets into bounded sets in C of JR. So for that, we define one set here B epsilon. Y belongs to C of JR such that the norm of y is less than or equal to epsilon. So we consider y belongs to B epsilon and we calculate the norm of Ty. So by putting the value of Ty and by taking norm, we observe that this norm is less than or equal to L, where the value of L is defined here. So the T maps bounded sets into bounded sets in C of JR. Now in step 3, we show that T maps the bounded sets into the equicontinuous sets of C of JR. So for that, we consider the 2 point T1, T2 belongs to J, with the T1 is strictly less than T2 and Y belongs to B epsilon. So by calculating this term, norm of Ty of T1 minus Ty of T2 and further simplifications, we get here this norm Ty of T1 minus Ty of T2 is less than or equal to this term. But as we observe that the right hand side tends to 0 as the T1 tends to T2. Hence, by Arzelov-Scully theorem, T is a completely continuous. Now in step 4, we show that the set defined here gamma is bounded. So for that we consider one point y belongs to gamma. So y is of the form lambda into Ty. And we calculate the norm of y. So further calculations, we get that norm of Ty is less than or equal to beta, where the value of beta is here. Therefore, we conclude that by Schafer's fixed point theorem, our given problem has at least one solution. Now in this section, we discuss the Ulam stability of the given problem. For that, we given here the definitions related to the Ulam-Heyer stability, Ulam-Heyer generalized stability, Ulam-Heyer's Raysier stability, and Ulam-Heyer's generalized Raysier stability. So theorem 5 tells us that if the assumptions H1 to H3 and the equation number 4 are satisfied, then the given problem is a Ulam-Heyer stable. So to prove this result, we use here the Passpatte's inequality, and by using this Passepartout inequality, we show that the given problem is a Ulam-Heyer stable. So this now at the last, we give one example to illustrate our result. For that, we define example represented by equation number 10 and 11, which is similar to the given problem with alpha equal to 0.6 and xi equal to 1/6. So we check here the hypothesis H1, H2, H3, H4. So all these hypotheses are satisfied, so that we find the value of delta here. And we observe that the value of delta is strictly less than 1 after some calculations. So by theorem 3, we conclude that the our problem 10 to 11 has a unique solution on closed interval 0 to 1. So these are some references which we have used in this paper. Thank you, sir.
Okay, thank you, madam. Next, Mrs. Jyoti Mashale, madam. Are you present? Hello, Jyoti Mashale, madam. Okay, okay, madam. Unmute yourself. Please start your camera.
So there is problem to the video.
Okay, then you can turn off your video.
Yes.
Okay.
Sir, check, is the screen visible?
1 minute. Screen is visible, but not your PPT. Please select your PPT and open it.
Sir, now please check.
Yes.
Yeah. Good afternoon to the respected chairperson of this session, Dr. Sajni sir, all the dear participants. Myself, Dr. Jyoti Mashale, from Punyashloka Ahilyadevi Holkar, Solapur University, Solapur, presenting a research work on the topic entitled Contemporary Research on Soft Graph Theory in this National Conference of Recent Trends in Mathematics and Statistics. Soft set theory actually is a new concept introduced in mathematics, which actually works as a generalization of fuzzy set theory, introduced by Professor Lafti-Zadeh in 1999, which deals with the uncertainties arises in the daily life. In this concept, he has given the generalization of fuzzy set theory. Later, some of the mathematicians have worked together. They have made a combination of the soft set theory along with the classical graph theory, and a new concept of soft graph was introduced. In this paper, we were going to give some new results on this concept of soft graph. Before that, we will just see the definition of soft set. Soft set is actually, if let U be a universe and E be the set of parameters, P of U denotes the power set of U. Then the pair HC is called as a soft set, where H is the mapping given by H defined from S to power set of U. In other words, we can say that this U is a parameterized family of subsets of the universal set, or you can say it is an epsilon approximate elements of the given soft set. Similarly, a soft subset is defined. Coming towards the main aspect of soft graph, if G equal to VE be a simple connected graph, C be a non-empty subset of V, R be an arbitrary relation between the elements of C and elements of V, then a set valued function f defined from C to power set of V is defined with f of x equals to collection of those vertices y in V where x is related to y. Then this pair FC is called as soft graph if each f of x is a connected subgraph of G. Let us just discuss with this as a simple example. Let this be a graph, simple graph, and we were considering the set V to be V1, V2, V4, and defining a set valued function say f of x, where we were collecting all the vertices which are at a distance less than or equals to 1. Then the three vertices set we will consider FV1, FV2, and FV3. If we plot the graph of all these, FV1 looks like this, FV2 and FV3, and we can see all these graphs are connected. Therefore, this FC is a soft graph. In the same example, if we change the relation less than or equals to 1 to equal to 1, then the graphs will look like this. This is f of V1, and which is not connected, hence it will not be a soft graph. Later, we have defined the degree of a vertex of the soft graph, and it was defined to be maximum of degree of the each vertex with respect to f of Vi, and it is called as the degree of vertex in soft graph. Similarly, we will define the degree matrix where the diagonal entries will be the degrees of the vertices. Adjacent to vertices, any two vertices Vi, Vj in this soft graph are said to be adjacent if one of the condition holds, that if this double tensor Vi, Vj is in the intersection of Fvi and Fvj, or if Vi is in f of Vj, if Vi is in A, Vi is not in A and Vj is in A. With this, we can check with the help of an example that how the graphs adjacent vertices of the graph looks like. I'll just keep the examples due to a time constraint. Coming to the next point of adjacency matrix of a soft graph. Adjacency matrix of soft graph was similarly defined to be the adjacency matrix of graph, where the entries gives you 1 if Vi is adjacent to Vj, and the entry is 0 if it is not adjacent. With example, we will discuss. This is the graph, and soft graph was constructed with the help of 2 points, V1 and V6. This is the graph for FV1 and this is the graph for FV6, and this will be the adjacency matrix for the corresponding soft graph. Similarly, incidency was defined with the entries as 1 if the edge Ej is in f of Vi, and the entry will be 0 otherwise. And this is also one example I have stated. Coming to the important results regarding this matrices soft graph. If G be a simple connected graph and C be a subset of V, FC be a soft graph given by f of x equals to collection of all those Z in V which are at a distance less than or equals to 1, then for V in C, sum of corresponding row elements in the adjacency matrix of A of FC is degree of the corresponding vertex with respect to soft graph. This is first important result we have obtained. The second one is we have written one remark in the above theorem. If V does not belongs to C, then this theorem will not hold. That is, sum of elements of the corresponding row is not equals to the degree of the matrix. This is an example we have discussed. Coming to the next result theorem. For a Peterson graph, we have stated this result. If G be a Peterson graph and Fs and Ft be the soft graphs of G, given by S is a collection of V1, V2, V5, T be a collection of V6 to V7, then row total of adjacency matrix is equals to degree of V with respect to soft graph. This is actually a Peterson graph, and we got the same result. And in the above theorem, if we take Q and V to be any arbitrary subsets of V, where Q is not equal to S and Q is not equals to T, then the above theorem will not hold. That is, row total of adjacency matrix need not be equals to the degree of a corresponding vertex. Just to verify this remark, we have stated one example. We have taken a Peterson graph and we have taken Q to be not S and not T, and we have checked out the result. And here you can observe very easily that degree is not equals to the row total is not equals to the degree. Coming to the next important result, which tells us actually for a simple connected graph, if F is a soft graph of G, A be an adjacency matrix, then A raised to K, which actually denotes the K times matrix multiplication of A, then number of walks from Vi to Vj in Fg of length K is at most Dkij, that is ith entry of the matrix AK. This kind of result was not true because in classical theory the result holds A plus D is equal to I into I transpose, but in soft graph the result do not hold. Just to check, we have produced one example. That's all. In this paper, we have tried to given some important notions regarding adjacency and incidency matrices, and we have proved some classical results. And these are some of the references used during the research. Thank you, sir.
Thank you, madam. Next number, Dattatreya Shinde, sir. Dattatreya Shinde, sir.
Yes, sir. Hello.
Okay, yes, you are audible.
Yeah. Yes.
Start
sir.
your
Thank you, sir. Sure, sir. Sure. Yes, sir. Hello, sir. Yes, sir.
Yes,
My screen is
your
visible.
screen is visible, sir. 1 minute.
Okay.
All other paper presenters, I am using chat box for the purpose that what will be the next number. You have to see the chat box and reply along according to this. It will be useful for communication. Okay. Thank you, sir. You can start now.
Okay, sir. Thank you, sir. First of all, good afternoon to all. My name is Dattatreya Shinde, and today I'm going to present a research article under the guidance of the Dr. M.T. Gophne, Shivaji University, Kolhapur. The title of my research article is on topological space of ternary semigroup. The abstract of this paper is, in that paper, we introduce and study the topological space of the ternary semigroup, and which is formed by the prime ideals of the ternary semigroup. Also, we investigate the various topological properties of the set of all prime ideals formed by the set of prime ideals, such as compactness, connectedness, and separation axioms of this topological space. And as we know, in the 19th century, D.H. Riemann studied the literature of the ternary algebraic system. The ternary algebraic system is nothing but the particular case of an array semigroup. And so many results of the ternary semigroup has an analogous version for the n-array system. Similar way, the many authors, F.N. Simons and M. Shabbir and S. Bashir, studied the ideals of the ternary semigroups. M. Shabbir and S. Bashir in 4 introduced and studied the notion of the prime, semi-prime, and irreducible ideals in the ternary semigroup. The best paper of this my paper is the K. Yaskar in 5. He introduced and studied the concept of structure space of the ternary semiring. Just he give some basic concepts of the topological spaces, and he discussed or he studied the properties of the topological space of the ternary semiring. Similar way, the Yaskar and Yes Chattopadhyay in 6, he also discussed and studied the properties of the structure space of the ternary, sorry, not a ternary, this is for only gamma semigroup. So similar way, in that paper, we just take the one topology of ternary semigroup, and which is formed by the prime ideals, and we check these properties. This topology is a T0 or T1, or it is a compact or connected. Okay, for that we use these preliminary definitions. First definition is ternary semigroup. What is ternary semigroup? So this is a T. Suppose T is any non-empty semigroup, and we define the ternary operation on that, and it satisfied the associative law, so it become a ternary semigroup. Okay, so this is a zero element of ternary semigroup. These all are the basic definitions and basic preliminary we have to use for that making this paper. Okay, now for the main result. So topological space of the ternary group. For that, we have to define the one set. So for that, we take the P be the family of all prime ideals of T. So what is prime ideals? This is a definition of prime ideal. A proper ideal I of T, T is nothing but the ternary semigroup, is said to be prime ideal of T, provided if I1, I2, I3 are the ideals of T, and I1, I2, I3 contain in I, implies This implies I1 containing I, or I2 containing I, or I3 containing I. So this is a definition of prime ideal, and we take the set of all prime ideals of T, and for that we take the any subset A of P. We define A bar. So we define the A bar such that I containing P, and the intersection of it is an infinite intersection containing this I. And so from this A bar, we define the one function or mapping is A is a subset of P. P is nothing but the family of our prime ideals. Then the function A to A bar is a closure operator on S. And when this is a closure operator, if it satisfies the conditions, which conditions? The phi bar is equal to phi. According to this definition, we show these the things. Phi bar equal to, phi means empty set. The closure of empty set is a empty set. Then we show that the A is a subset of closure set. Then we show that closure of closure is equal to A closure. Then we show that the A, suppose A is a subset of B, then it's a closure also subset. A bar is subset of B bar. Similar way, we show that the A union B, closure of A union B is equal to union of closure. So then this operation, this mapping forms the closure. We call this is a, and we define the definition. The definition is the closure operator A to A bar induce the topology tau on P, that's it P, family of all prime ideals. This topology tau is called as a Hull kernel topology, and this topological space is called as a structure space of the ternary semigroup T. From that, we define the one set. Suppose we take the I is the ideal of T, and we define the X of I such that J belongs to P, such that I containing J, and we define the another set Y of I is the complement of this Xi. And next theorem is very interesting theorem is any closure set in P is of the form Xi. And in that theorem, we show that this Xi set is a closure of this P. And from this similar way, we state that its a complement is, means its complement is Y of I, is a open set. Okay, so in our hand, open set is there, closure is set there. And so we go to the another forms the basis. And this Y of A, the set Y of A belongs to T, forms the base of the open set for the topology tau of P. And this is simple result and the simple proof of this theorem. And for that theorem, just we use the corollary this 3.4. Okay. So next is very interesting result is the topological space P of tau is a T0 space. As for T0, we take the two elements of that set P. Okay. So I and J be the two elements of set P. And then there is an element A belongs to T is either in I complement or J complement. Assume that suppose we take the A is containing the I complement, but the J does not, J belongs to Y of A according to the definition. So then I does not belongs to Y of A, and that is Y of A is a neighborhood of J not containing the I. And then you can, by the definition of T0 space, hence our P comma tau topology is a T0 space. Similar way, you can show that this is a P comma tau topology is a T1 space if and only if no element of P containing the any other element of P. This is also one result. And from this result, we state the one corollary. If P of T is a Hausdorff space, then no prime ideal containing any other element on any other prime ideals. Alternatively, we say that if the space P comma tau is a Hausdorff space, then the set of all minimal prime ideals and maximal prime ideals are coincide. This is a very simple corollary. Now we define the maximal ideal, and proper ideal I of T is said to be maximal ideal of T if it has not properly containing any other proper ideal of T. This is a basic definition for the maximal ideal for the ternary semigroup T. And now for that, we state the one corollary. Suppose we take the M, capital M be the set of all prime proper maximal ideals of a ternary semigroup T with identity. Here we take the with identity, and then this M comma T Tm is a tau M is a T1 space where tau M is the induced topology on M from P comma T. Similar way, we state the one result. If P of T P of tau is a Hausdorff space containing more than one element, then there exist two elements belongs to that ternary semigroup such that P is equal to Y of A is our open set union Y of B is also open set union X of I. X of I means This is a closure set where I is the ideal generated by A and B in T, and this is a result. Okay, from this result we state the theorem 3.13. Okay, so this is a proof. Now next thing is now we going towards the compact space. The topological space P comma tau is a compact space if and only if the collection, all collections AI where there is an index set of T, there exists a finite sub collection. Here there exists a finite collection A1, A2 up to so on AN in T, such that I belongs to P. There exists a AI such that AI does not belongs to I. And this is a proof for this. I'm not going to detail. Okay. So next thing is, if T is a finitely generated, then the space P comma tau is a compact. This is also very simple result. Now next thing is a very important thing in the prime related to the prime ideal. The arbitrary intersection of all prime ideals of T is the semi-prime ideal of T, provided it is non-empty. But we give the necessary condition for the intersection. Here we know that the arbitrary intersection of all prime ideals of T is a semi-prime ideal. But now here we state the necessary condition, the intersection of prime ideals of T to be prime ideal, and is the following theorem. This is the following theorem. Just I am putting the one restrictions here, or I am putting the one conditions here. Which condition? So let I of I be the family of all prime ideals of T, such that the set II forms the chain. Chain is important, and then it's an infinite intersection, or this arbitrary intersection become a prime ideal. And this is simple proof related to the for this theorem. And now we define the nextly is a irreducible pseudosymmetric irreducible topology. So this is a proof of this theorem. Then we discuss about the subset U of P is a dense in P if and only P of U is equal to R of P. Okay. So one more thing is we define the Noetherian ternary semigroup, and we show that this Noetherian ternary semigroup is a second countable. Okay. And these are the references we have to use for the preparing this manuscript or research article. Thank you. Thank you to all.
Thank you, sir.
Okay, thank you so much.
Now, Ms. Shinde Sunita Sanjay. Are you ready? Shinde ma'am?
Yes, sir.
Okay. Unmute yours. Start your presentation, ma'am.
Yes. Good evening, everyone. I am Sunita Shinde from the Department of Mathematics, YCIS Satara. I am here to present the research paper entitled with Alternative Method for the Dual Fully Fuzzy Linear System by using the Kraut method for the coefficient matrix. In this paper, we will discuss an alternative way to solve a fully fuzzy linear system using a Kraut method of the form A tilde cross x tilde plus b tilde is equal to c tilde cross x tilde plus d tilde. In this paper, we will discuss an alternative way to factorize matrix A tilde and C tilde by using the Kraut's method. We will compare the example given by the Moshadi after factorization of by Kraut's method. Here is some definition regarding to our paper. In this section, we discuss the algebra of a triangular fuzzy number. The multiplication, addition, and subtraction of fuzzy number are given by equation A, B, C, D, and E. Here is a theorem to represent the product of two fuzzy number. Here is our main result. Let us consider a dual fully fuzzy linear system given as follows. Then we firstly factorize the matrix A into lower triangular matrix and upper triangular matrix by using Kraut's method. Similarly, factorize matrix M, N, C, K, L by using the Kraut's method. Then we have to determine the factor F, P, Q by using algorithm, and therefore find the values of X, Y, Z as given in equation 2. Here is a computational example regarding to our algorithm. In equation 3 gives the fully fuzzy linear system. With after comparison, we get the matrix A and C. Then we factorize the matrix A and C into lower triangular and upper triangular matrix with using Kraut method. Then we will obtain the matrices 2 star, U3 star and U2 star dot U3 star dot as given below. Then we have to find the factor F tilde. Then for that we need to find F1 tilde and F2 tilde. F tilde is equals to RST is equal to matrix 2, 2, 3, 6, 4, 4. Then we have to find X, Y, Z using the formulas. The X is equals to 2, 1, Y is equals to 1, 1 by 2, and Z is equals to 4 minus 2. Hence, we have the solution X1 tilde is equals to X1, Y1, Z1, that is equals to 2, 1, 4. X2 tilde is equals to X2, Y2, Z2 equals to 1 minus 1, 1 by 2 minus 2. To check the validity of the solution, we substitute back X1 tilde and X2 tilde into original equation number 3. Hence, we see that the result is valid. The conclusion of this paper is we gives an alternative way to factorize coefficient matrix A tilde and C tilde for the solving the dual fully fuzzy linear system. Here is some references regarding to our paper. Thank you.
Thank you, madam. All the paper presenters, you have to constrain your time because we are already late. Please conclude yourself within 3 to 4 minutes. Next one is Rohini ma'am. Are you present?
Yes, sir.
Okay. Start your presentation, ma'am.
Good evening. Good evening.
Yes. Ma'am, your screen is not seeing properly.
Now is it okay, sir?
Yes.
त्यांचं मिनिमाइज करतो मी आपलं ओपन करून ठेवतो.
Can I start?
Yes.
Good evening, all. Myself, Rohini Mane from Department of Mathematics, YCI Satara. Now I am going to present our paper entitled with existence and uniqueness of solutions for nonlinear differential equations with non-local integral equations. The objective of this paper is to establish existence and uniqueness of solutions for nonlinear algebra fractional integral differential equations with non-local integral boundary conditions with the help of Banach contraction principle and Schauder fixed point theorem. We consider the problem for nonlinear local integral boundary conditions. Equation 1.1 is the given defined problem where alpha and t of order alpha y of t is the remaining wholly fractional derivative of the function y of t. F is continuous functions. The problem 1.1 is equivalent to the following integral equation 1.2. That is, the solution of the integral equation 1.1 is the solution of the problem 1.1 and vice versa. These are some basic definitions and lemma which we have used in this paper. Now we are moving to main results. Existence and uniqueness of solutions of problem 1.1. Theorem 2 is based on Schauder fixed point theorem. If the hypothesis A1 and A3 are satisfied, then the proposed problem has at least one solution on J. Proof of this theorem consists of 4 steps. In step 1, we show that the operator T from Banach space of all continuous functions J to R to Banach space of all continuous functions J to R, which is defined in equation 2.2, is continuous. We use here the sequential criteria of continuity. For that, consider yn such that yn tends to y in C of JR.
तुला सही आहे ना हा मग अर्ज देऊन जावं
T minus Ty of t. After some calculations and continuity of f, we get norm of Tyn minus Ty tends to 0 as n tends to infinity. Hence t is continuous. In next step, we show that the T maps bounded sets into the bounded set in C of JR. BR equals, for this we define a set BR equals to y belongs to C of JR such that norm of y is less than equals to R. By using hypothesis A2 and equation 2.2, we get the norm of y is less than equals to I. Value of I is defined here. T maps bounded sets into the bounded sets. In third step, we show that the T maps bounded set into the equicontinuous sets of C of JR. For T1, T2 belongs to J with T1 is greater than equal, less than equal to T2 and Y belongs to BR. We consider the term mod of Ty T2 minus Ty T1, substituting the corresponding values, and after simplification, we arrived at this step and we observe that as T1 tends to T2, the RHS of above inequality tends to 0. By Arzelais-Colli theorem, we get T is completely continuous. And last step, we prove T of BR is subset of BR. For that, we consider Y. Then we show that T of BR belongs to BR. For T belongs to D, then by condition A2 and equation 2.2, we have by inequality norm of Ty is less than equal to T of BR is subset of BR. And now applying Schauder fixed point theorem, we conclude that there exists at least one fixed point Y of T in C of JR. This fixed point Y is the solution of problem 1.1 on Now the theorem 3 is about uniqueness of problem 1.1. To prove this theorem, we consider hypothesis H1 is hold and the Z is strictly less than 1, which is defined here. Then the proposed problem 1.1 has a unique solution. To prove this theorem, we define an operator T from C of JR to C of JR as given here equation 3.2. By using Banach contraction principle, we show that T has unique fixed point. So for that, we consider norm of Ty1 minus Ty2 is equal to supremum T belongs to J, norm of Ty1 of T minus Ty2 of T. After solving this expression, we get here norm of Ty1 minus Ty2 is less than equal to Z of norm of Y1 minus Y2. But from given condition, Z is less than equals to Z is strictly less than 1. This shows that T is contraction map. So it has unique fixed point. So problem 1.1 has unique solution. These are references we have used. Thank you, sir.
Okay, thank you, madam. Next number is Kazi sir. Are you ready, Kazi sir? Hello, M.A. Kazi sir. Hello, Kaji sir is there. Next, Gajare Amarjit sir.
Yes, present.
Okay, you can start, sir. Kaji sir will present after then.
Okay, sir. Good evening, all. Good evening, all. I am Amarjit Gajare from Department of Mathematics, YCS Satara. I am going to present our paper entitled with existence and uniqueness result for the non-linear mixed fractional integral differential equation with a non-local boundary condition. In objective for this paper is establish the existence and uniqueness of the solution non-linear mixed fractional integral differential equation with a non-local boundary conditions. Our aim results are demonstrated with help of the Banach and Krasnodębski fixed point theorem. In this paper, we are considered following fractional differential equation represented by 1.1 with a non-local condition represented equation 1.2 here 0 less than sigma j less than xi of I less than 1 and P and Q lies between 0 to 1. CTP and CDPQ are the capable fractional derivative and
गर्जे सर आवाज येत नाहीये.
GS, K and are the continuous function. These are the some elements which we have used to prove our main result. This is our some lemmas with the help of Krasnov-Samirsky fixed point theorem are to our existence result. These are the one of the most important lemma which tell about why is the solution of a given problem 1.1 and 1.2 if I believe y satisfies this integral equation here p and q lies between 0 to 1 and g h k are the continuous function. To prove the result, we operate integration of
Excuse me, sir. Hello. Gazare sir. Hello, Gazare sir. 1 minute.
Hello.
Gazare sir, you are not properly audible. Is there any problem in mic or anything?
No, sir.
Okay, start now. Now you are properly audible. Okay.
Okay, sir. To prove this result, we operate integration of a order Q on both sides of equation 1.1. So after performing this stage, we obtain equation 1.9, 2.9 and 2.2. Now we prove existence of solution of a given. To prove this result, we use these two hypotheses H1 and H2, which are given here. Now we fix R bar greater than equal to lambda into norm of psi, and we consider this fixed closed form. B R bar is equal to y belongs to C such that norm of y is equal to R bar. For that, we define the operators P1 and P2 on BR as represented here for y1 and y2 belong to BR bar and P belongs to closed interval 0 to 1, and by the assumption H2 is the kind norm of P1 y1 plus P2 y2 less equal to psi into lambda of R bar. This implies that P1 y1 plus P2 y2 belongs to BR bar. Now we prove P2 is a contraction of that we consider y1, y2 belongs to this of the all continuous functions from closed interval 0 to 1 to R. For that we consider norm of P2 minus P2 y1 minus P2 y2. After the calculation, we observe that this is less than equal to m into lambda 1 norm of y1 minus y2. But m into lambda 1 less than 1. Therefore, P2 is a contradiction. Hence, G, H, K are continuous function. Therefore, P1 is a continuous, and hence P1 is a uniformly bounded on BR bar as here. With the help of hypothesis H1, we prove the compactness of an operator P1. For that, we define the G bar, H bar, K bar, H bar as given here. Then for 0 less than equal to tau less when tau we obtain this term. Hence, by the Algera-Ascoli theorem, P1 is a compact on BR bar. Hence, the given problem has at least one solution. Now, we prove uniqueness of a solution of given problem by using Banach fixed point theorem. Statement of theorem is if the assumption H1 is a true along with m into lambda strictly less than 1, then a given problem has a unique solution. For that, we define m is equal to maximum of m1, m2, m3, m4 here, m1, m2, m3, m4 are given here. For that, we fix r greater than equal to m lambda upon 1 minus m lambda and consider b I is equal to y belong to C such that norm of y strictly less than equal to R. Thereby, using hypothesis H1, this now we will show that TPR subset of BR for that we consider y belongs to BR and calculate norm of TPR. So after calculation, we get is less than equal to R. Therefore, TBR subset of BR. Now we show that T satisfied Banach's point theorem. For that, we consider y1, y2 belong to base of the odd condition continuous function close to equal to 0 to 1 to R. Consider norm of Ty1 of T minus Ty2 of T. So after calculation, we get this less than equal to m into lambda norm of y1 minus y2 for m into lambda 1 strictly less than 1 and Banach's point theorem that the operate T is conjunction then there exists solution of a given problem. These are the some references which we have used. Thank you.
Okay, thank you, sir. Kazi sir, are you present? Kazi sir? Dayanand Vyavahare sir?
Yes, sir.
Okay.
I'm
Start your
audible, sir?
presentation, sir.
Okay, sir. Thank you, sir.
Next number Shivraj Thate sir. You have to present after this.
My screen is visible, sir.
Yes. Please start your presentation.
Good afternoon, everyone. My name is Dayan Kalyan Vyavahare. Today I am going to present my article, discuss the existence and uniqueness result for nonlinear fractional differential equation with delay under the guidance of Dr. G.V. Kharat, sir. In my abstract, this paper studies nonlinear fractional differential equation with delay containing fractional derivative inclusion of order beta, and here fractional derivative considered is in the form of kappa-2 sense. We discuss the existence and uniqueness result of solution of using fixed point theorem. The outlines of my topic: introduction, preliminaries, existence and uniqueness of solution. And
Vyavahare sir, your presentation is not visible.
wait,
Sir,
ma'am.
your screen is visible, but not your presentation. Please start your presentation.
Okay, sir. I will try again. Yes, sir. Now
Yes.
my screen
Yes, yes.
is scrolling right now.
Okay, you have to continue now.
This is in this abstract. This paper studies nonlinear fractional differential equation with delay differential equation with delay containing fractional derivative inclusion of order beta, and here fractional derivative considered here in kappa-2 sense. We discuss the existence and uniqueness result of this problem by using fixed point theorem. Outlines of my topic: introduction, preliminaries, and existence and uniqueness of solution. In the introduction, fractional calculus is an extension of ordinary calculus, and ideas of fractional differentiation and integration use the related name of Liouville. And fractional differentiation and integration have several uses and certain requirements. This is the introduction part, and I have motivated from the problem this Yufeng Zheng and Zheng Zheng presented existence and uniqueness solution of boundary value problem of nonlinear fractional differential equation. They have considered this problem, and this is the kappa-2 derivative of order beta, and beta is lies between n minus 1 to n. And another paper I have studied, Syed Abbas, they have to prove existence and uniqueness solution of fractional order ordinary and the differential equation. By motivating this work, I have taken the problem. We have shown that existence and uniqueness solution of this problem. This is the kappa-2 derivative of y of t of order beta is equal to f of t y of t. Here y of t is a delay operator and tau is a delay, and this is the initial condition, and this is an so condition we have taken, and f is a continuous function from this to this. for this problem, we have discussed about this problem as existence and uniqueness result by using the fixed point theorems, by using Banach fixed point theorem and Schroeder fixed point theorem. Also, we have some definition, basic definitions that we have need. So this is the definition of Riemann level fractional integral of order nu of function f of z. This is the Riemann level fractional integral, and also we have need the Capetto fractional derivative of order nu. This is the Capetto fractional derivative defined like this, and also need lemmas. This lemma is refer from 9. The Capetto derivative of z of t is equal to 0 has the solution like this, and also Capetto integral of Capetto derivative of z of t is like this. So first we find our problem is like this. First we find equivalence integral equation of this problem is like this. So we have to find existence and uniqueness solution of this problem by using Banach fixed point theorem and Schroeder fixed point theorem. So first my result is if function f is from 0 to t c to r is a continuous function, and that is satisfied this condition, that is like Lipschitz condition of f, and problem 2.1 has unique solution provided that this condition. We have to prove this theorem by using Banach fixed point theorem. First we define operator a of t is equal to like this, and by using Banach fixed point theorem we can easily say that this problem has an unique solution. Also, we take a second theorem. Assume that if your function f is from 0 to t cross c to r is continuous function. Also, there exists one condition. Also, there exists m greater than 0, such that m is defined like this: supremum of s belongs to 0 to t, and y of s belongs to c of f of s y of s. So this theorem we prove by using Schroeder fixed point theorem. First, we prove continuous. This our operator defined here a y of t is equal to this is continuous. After that we will prove operator a is a map bounded set to bounded set, and after that we have to prove this operator is equicontinuous. Then by we say that by Arzelà-Ascoli theorem our operator a is an completely continuous. Then operator is completely continuous, and then by then the Schroeder fixed point theorem we can say that our function f has fixed point. Our function has fixed point means our problem has at least one solution, that is problem has a solution. So these are the references that I have used in my article. So thank you, sir.
Okay, thank you, sir. Now Tate sir will present.
Am I audible?
Yes, sir. Please start your screen.
Hello. Am I audible?
Yes, you are audible, sir. Please start your screen. Vyavare sir, you have to close your screen. Tate sir, your screen is visible now. Please start your presentation. Kazi sir will present after this. Then Shelke Sheetal ma'am.
Hello, sir.
Yes.
Hello. I'm trying to share my screen, but message is appearing. You cannot start screen sharing while the other participant is sharing. Okay, I'm trying.
Vyavare sir, have you closed your screen?
Yeah. 1 minute. Ah. 1 minute, sir. Is it appearing my screen?
1 minute, sir.
No.
No, sir.
Wait. Now?
No, sir. Still not seeing the screen. Is there any problem? You can.
Yes, yes. Right now it is appearing.
Not 1 minute. Yes, 1 minute.
Right. Now is it appearing?
I think so. There will be network issue. Because
No,
we are seeing that you have Dr. Shivaji Tate has started screen sharing, but not visible your screen.
now I can
Maybe network
see my
problem, sir.
present.
Otherwise,
can
you
see.
can present yourself through your talk. Is it possible, sir?
Okay.
Because time is too much.
Sir, I can see my presentation right now. You are sharing screen.
1 minute. Other participants, are you visible your screen of Dr. Tate, sir?
No, sir. Screen is not visible.
Screen is not visible, sir. Tate, sir.
No, sir. Screen is not visible.
Something will be wrong there. Are you trying again? Because next presenter is ready to present. Hello, sir. You have to leave the meet and join again. You can present after Kazi, sir. Is it possible? Tate, sir.
ताटे सर, तुमचा व्हिडिओ फक्त बंद करा आणि फक्त शेअरिंग करा म्हणजे दिसेल. नेटवर्क इश्यू दिसतोय.
हा, नेटवर्क इश्यूज आहे. काझी सर. Hello. Kazi sir, you can present. Tate sir will present after your presentation. Kazi sir. Hello. Kazi sir, are you ready? I think so. You are having also. Yes. Okay. Your screen is visible, sir. Kazi sir, you can start your presentation. You are not audible, Kazi sir. Kazi sir. Hello. Kazi sir, you are not audible. We are seeing your screen only. Hello, Kazi sir, please reply. You can use chat box for that purpose. Otherwise, Shelke madam is ready. Hello. Kazi sir, are you audible? Kazi sir, you are not audible because also Madhvi ma'am has stated that you are not audible. Your voice is not coming. Is there any problem? But you are not audible. I think so. If you are using cord, you can switch off your cord and talk without any cord. Please check chat box, Kazi sir. You are not audible. I have disconnected. Okay. Shalke ma'am. Shalke ma'am.
Yes, sir.
Okay. You are audible. Start your screen. I think so. Kazi sir is out of coverage or out of network. Whether your screen is visible, please share your screen.
Okay, sir.
Okay. Kazi sir, please off your screen. I am.
Yes, ma'am. You are audible. Your screen is not visible. Kazi sir.
I am unable to share.
Are you hearing? Kazi sir, we are audible. Please turn off your screen. Okay, madam. Now you can present yourself.
Okay, sir. Okay.
Yes. Your screen is visible now.
I'm Kazi sir.
Hello.
1 minute. Kazi sir, now Shalke ma'am is presenting.
Okay, sir. Good evening, all. I am Sheetal Shalke from Department of Mathematics, YCIS Satara. I'm going to present my paper entitled with the new integral transform and its application to boundary value problem and integral equations. So in this paper, we introduced a new integral transform and discuss some operational properties of this integral transform. And further, we prove some theorems. Our integral transform is extension of Mahgoob transform, Mohan transform, Rohit transform, and Dinesh Verma transform. So the definition of new integral transform is if f of t is piecewise continuous on an interval 0 less equal t less than or equal to a and of exponential order alpha, then v of f of t is equal to p raised to alpha integration from 0 to infinity e raised to minus pt f of t dt, where v is a new integral transform operator and p may be real or complex, alpha is any real number. For that, we defining this new integral transform. And if we putting alpha equal to 1, we get Mahgoob transform. For alpha equal to 2, we get Mohan transform. For alpha equal to 3, we get Rohit transform. And for alpha equal to 5, we get Dinesh Verma transform. Now, some operational properties of new integral transform. That is the new integral transform of some standard function we have listed below. Now the definition of inverse transform of new integral transform is f of t is equal to v inverse of f of t, and some inverse transform of some standard function we have given below, and some theorem. If f of t is differentiable, then we get this. And with the help of given properties, we can easily prove this theorem. And this is theorem 2. If v of f of t is equal to f of t, then this is multiplication by t theorem we have verified here. And the conclusion of this paper, we have introduced the new integral transform which can be used for solving differential equations and integral equations effectively. Thank you, sir. And these are the references we have used in this paper. Thank you, sir.
Okay, madam. Next number, Dr. Tate sir or Dr. Kazi sir.
Hello.
Hello.
Sir. I am joined again with the help of mobile. So
okay, Kazi sir is speaking. No, Tate sir. Okay.
I'm showing
Okay.
my presentation on mobile.
Okay, okay. Start your screen.
Okay, is it visible?
Yes. Please share your screen. Screen is visible, but not your presentation.
Okay, okay.
Please use horizontal mode, sir. Auto rotate. Hello.
Is it not showing PDF?
1 minute. Not yet. You are
PDF,
searching
PDF.
someone.
Now it is showing PDF or not?
Yes, yes, PDF is showing.
Okay, okay. Horizontal. Okay, now it is showing title.
Okay. Yes, sir,
Okay,
visible.
myself, Dr. Shivaji Tate. I am head of Department of Mathematics, Kishanwir Mahavidyalaya, Vai. My title of paper is Existence and Uniqueness of Solution for Non-Linear Fractional Relaxation Differential Equation in terms of Caputo fractional derivative. This is my outline of the paper. Abstract. In this study, we examine the existence and uniqueness of solution for non-linear fractional relaxation differential equation involving Caputo fractional derivative with non-local condition. So to prove the existence of solution, we use the Krasnoselevsky fixed point theorem, and to prove uniqueness of the solution, we apply the Banach contraction principle. And last one illustrative example is given to demonstrate our result. As we all of you know, the fractional calculus is an extension of the ordinary differential differentiation and integration to the arbitrary non-integer order, and it have many applications in various fields such as science, engineering, economics, controls, systems, etc. These are some references. There are many authors studied the various properties of fractional differential equation. For example, Chido and co-authors discuss the existence and uniqueness for positive solution of the nonlinear Caputo fractional relaxation differential equation. Adjodi and co-authors studied positive solution of nonlinear Caputo fractional derivative. Simab and Rehman investigated the existence and stability. So, inspiring the above work, we consider here problem equation number 1. Here derivative is Caputo fractional derivative. Alpha is the order, is in between 0 to 1, and omega is greater than 0. F, G, and H are continuous functions. So this kind of problem, non-local Cauchy problem, introduced by Bayezewski. We consider here this example of non-local condition, H of U equal to summation I equal to 1 to P, Ci, U of Ti. Ci are all constant, and Ti are in between 0 to T. To prove our result, we first transform the problem into integral equation, and we use Krasnoselevsky and Banach's fixed point theorem. Here are some preliminaries which we use in our next parts of the paper. We use here a norm, sup norm. First definition is the Riemann fractional integration. It is defined by equation number 2. Next definition is Caputo fractional derivative of order alpha, equation number 3. Next definition, 2-parameter function of Mittag-Leffler type is defined by the expansion of series equation number 4. If we put beta equal to 1, then this Mittag-Leffler function of 2 variable transform into the one parameter, like equation number 5. Next is lemma 4. For t belongs to close and open interval 0 to infinity, and alpha belongs to open close interval 0 to 1. The 1 parameter Mittag-Leffler function E alpha comma 1 of minus t raised to alpha is a decreasing function of t, and it is bounded from above by 1. That is equation number 6. And if we take a limit from t to infinity, then it will become 0. Next preliminary, theorem number 5 is Banach fixed point theorem. And theorem number 6 is Krasnov-Szymanski fixed point theorem. As the previous researchers also use these theorems for their problem. Next, we transform the problem number 1 into the integral equation. Lemma number 7, let u belongs to space of continuous function from J to R, and let u dash exist. Then u is the solution of problem 1 if and only if it is solution of integral equation number 8. I skip all the proofs. So this, to prove this lemma 7, we use Laplace transform. Next, we assume some hypothesis H1. There exists a constant LF belongs to R plus such that the modulus of f of t comma u minus f of t comma v is less than or equal to LF into modulus u minus v for t belongs to J. J is closed interval 0 to t. U comma v belongs to R. Next, H2, there exists constant L, G belongs to 0 comma 1 such that modulus of G of t comma u minus G of t comma v is less than or equal to LF into modulus of u minus v for t belongs to J and u belongs to R. H3, there exists LH belongs to 0 to 1 open interval such that h of u minus modulus of h of u minus h of v is less than or equal to LH into modulus u minus v for each uv belongs to space of continuous function from J to R. In next theorem, we prove the uniqueness for the problem, uniqueness solution for the problem 1. Assume that the assumption h1 to h3 are satisfied, and if the equation number 9 is satisfied, then there exists a unique solution for problem 1. To prove this, we use integral equation as an operator, continuous phi from Cj comma R to Cj comma R. By equation number 10, and by using H1, H2, and H3 hypothesis, we get inequality 11. And so the from 9 number inequality, phi is a contraction, and by Banach fixed point theorem, this phi has fixed point, unique fixed point, which is the solution of problem 1 on J. Next theorem, assume H2, H3 with LH plus LG is less than 1, and the following hypotheses are satisfied. That is H4, there exists P1 belongs to C such that modulus of f of t comma u is less than or equal to P1 of t for t belongs to J and each u belongs to R. H5, there exists P2 belongs to C such that modulus of G of t comma u is less than or equal to P2 of t for t belongs to J and for each u belongs to R. And H6, there exists P3 such that P3 greater than 0 such that modulus of h of u is less than or equal to P3 for t belongs to J and each u belongs to R. Then the problem has at least one solution is omega. To prove this, we first fix rho is greater than this quantity equation number 12. P1 star is the supremum of P1 of t, P2 star is the supremum of P2 of t, and Q is the supremum of G of t comma u. And we consider the non-empty closed convex subset omega, and we define, as per the Krasnov-Szymanski fixed point theorem, we have to define two operators. So we define these two operations, equation number 13 and 14. And as per the Krasnov-Szymanski fixed point theorem, we satisfy all the conditions of the Krasnov-Szymanski fixed point theorem. So according to Krasnov-Szymanski fixed point theorem, to prove that there exists at least one fixed point for the operator f1 plus f2 in omega, and this proof contains several steps. Step number 1, we prove f1 of u plus f2 of v belongs to omega for all uv belongs to omega. Step 2, f1 is compact and continuous, and step 3 is f2 is contraction mapping. Next, we introduce one example to demonstrate our result. We consider the problem number 15, where Ti is in between 0 to 1 and Ci are all constant with summation of I equal to 1 to n. Ci is less than or equal to 1 upon 5. If we then we compare the problem with our problem, and we get t equal to 1, u0 equal to 1 minus summation of I equal to 1 to n ci u of ti, alpha omega equal to 1, g of t comma u equal to 1 upon 4 u cos t, and f of tu equal to 1 upon exponential function of t plus 4 into the bracket mod u plus 1. Now we check the hypothesis in our theorems 16, 17, and 18. And we get the assumption H1, H2, H3 are satisfied with LF equal to 1 upon 5, LH is equal to 1 upon 5, LG equal to 1 upon 4. And the condition given in theorem number 8 is satisfied. So the problem number 5 has a unique solution. These are these references. Thank you. Hello.
Okay, sir. Thank you. Next number, Dr. Kaji, sir. Are you ready?
Yes, sir. I'm trying to connect.
Is there still there any problem?
Yes, sir.
Okay, and otherwise Nitin Jagtap sir is ready to present.
Sir, continue with Jagtap, sir.
Jagtap sir, please start
Yes,
your
sir.
screen.
Yes, sir. Yes, sir.
Okay. After then, Dr. Nirmala Kautekar ma'am, you have to present. Okay, Jagtap sir.
Okay, okay. Good evening. I am Mr. Nitin Jagtap, sir, Department of Mathematics from Balwant College, Vita. My paper title is Fifth Order Boundary Value Problem for Random Differential Equation. Abstract is the boundary value problem for a fifth order random differential equation with a random solution is investigated. In this study, we use the generalized Lipschitz and Cathode conditions to apply the random fixed point theorem. Keywords are boundary value problem, random differential equation, random fixed point theorem, random Cathode conditions. Description of the problem. Consider boundary value problem for fifth order random differential equation as u fifth of tw plus f of utw is equal to 0 for 0 less than t less than 1 with conditions u double dash 0 of w is equal to 0, u dash of 1w is equal to u double dash of eta w is equal to u double dash of eta w is equal to u triple dash of eta w is equal to alpha for all omega, for all w belongs to omega, where f is a mapping from j cross r cross omega to r. Random solution of the problem. Here, corollary is BR0 and BR bar 0 be the open and closed balls centered at origin of radius r in the Banach space E, and let Q is the mapping from omega to BR bar 0 to E be a compact and continuous. Then the random equation Q of omega x is equal to x has a random solution, that is there is a measurable function eta is a mapping from omega to BR bar 0 such that Q of omega and eta of omega is equal to eta of omega for all w belongs to omega. This is another theorem. Here we get another lemma for any real number m greater than 0 and sigma belongs to L dash of j of r, x is the solution to the differential equation with conditions x double dash of t plus m square of x of t is equal to sigma of t almost everywhere for t belongs to jm. Here we another definition. Definition 2.2. A function f is a mapping from J cross R cross omega to R is called L dash random category if third for each real number R greater than 0. There is a measurable and bounded function QR is a mapping from omega to L dash of JR such that mode of f of t x omega is always less than equal to QR of t omega almost everywhere t belongs to J for all W belongs to omega and X belongs to R with mode of X is less than equal to R. Here main existence result is the function Fm is a random category on J cross R cross omega. There exists a measurable and bounded function gamma is a mapping from omega to L square of J of R and a continuous and non-decreasing function psi is a mapping from R plus to 0 infinity such that X omega is always less than equal to gamma of t omega into psi of mode of X almost everywhere for t belongs to J for all W belongs to omega and X belongs to R. Here we use another theorem. Assume that A1, A2 holds. Suppose that there exists a real number R greater than 0 such that R is always greater than e raised to 2m pi plus 1 divided by 2m into e raised to 2m pi minus 1 into norm of gamma W into L dash of psi of R. This is proof. In this way, here we would get proof. R is less than equal to e raised to 2m pi plus 1 divided by 2m into e raised to 2m pi minus 1 into mode of R of omega into psi of R. And these are references. Okay, thank you.
Hello, sir. I am audible.
Yes, yes.
Hello, thank you, sir.
Okay, okay.
Now, Kazi sir, are you ready?
Yes, sir.
Okay. You have to start your screen and start your audio. Okay.
Is it my screen is visible to you, sir?
Yes, 1 minute. Your screen is visible, but again,
I'm audible.
You are audible. There is no problem. But yours, yes, yes, sir.
So our research article proposed is the title is Existence and Uniqueness Solutions of Fredholm-Volterra type Fractional Integral Differential Equations with Deviating Arguments. So abstracts is we have considered the mixed type integral differential equations with conditions defined in the abstract. D alpha 0 plus U of t is equal to f of t u of t of theta of t comma integral 0 to t k of t of s u of s ds comma 0 to t integration h t of s u of s ds t belongs to j in the interval 0 and u of 0 is equal to lambda integral 0 to t u of s ds plus d where t belongs to r. So introduction this we have proposed one integral equation for the Riemann-Liouville fractional differential equation under the deviating arguments. We have formed the solutions for the equation 1.1 and we have given some preliminaries, that is Riemann-Liouville fractional integral, Riemann-Liouville fractional derivative, and some of the lemmas that we require to define the solution for the particular problem which is we have defined. This section we have proved the continuity of the problem of the function u of t, which is the solution of our problem 1.1. We have defined the uniqueness of the solution for the problem by defining some of the conditions, the theorem format, and we have imposed the lambda value less than this part, and we have shown the operator T defined on the function, and we have proved that the T contracts and it follows from the Banach fixed point theorem and shows that it has unique solution. And, one of the corollary we have defined, and that corollary obviously holds the following above properties of the theorem 3.1. Then in continue, we have shown the monotone iterative method to find out the solution for the particular problem. That we have defined the equicontinuity of the function. The function is continuous and converges for the sequences of the function by Argyla-Oskili theorem. And we have shown that the solution exists for what we have defined the integral equation. And lastly, we have defined one of the theorem, continue to that part, and also shows that it has maximal and minimal solutions to the particular problem. And also we have proved that the function has boundedness and follows the uniform continuity. And we have considered this is the this method to define the research problem. And we have shown that the research problem contains the unique solution for the different intervals and the properties. Some of the references we have used and we have shown here. Okay, sir. I'm audible?
Yes, audible.
Okay, ma'am. Yeah. So I'm concluding here itself.
Okay. नेक्स्ट पार्टिसिपंट कोण आहे त्यांनी पटकन आपली जॉईन व्हा.
हा येस मॅडम.
हॅलो हॅलो मॅम.
हॅलो.
हा कवटेकर मॅम.
हो हो जॉईन करते. हो
ओके ओके ओके.
हा
चालेल चालेल. ओके व्हॅलिडिटी घ्यायचं मॅम.
हो हो
ओके. व्हॅलिडिटी घेताय का? मी निघू का? कॉर्ड तुमची लावाल. ऑनलाईन जॉईन होते की आता काय व्हॅलिडिटी 5 मिनिट.
सर आधीची स्क्रीन अजून गेलेली नाहीये.
Wait a minute, ma'am.
काजी सरांची स्क्रीन बंद करायला पाहिजे.
हो मॅडम, आय एम क्लोजिंग द ऑप्शन.
स्टॉप शेअरिंग करा सर.
हॅलो
स्टॉप द शेअरिंग करा.
हॅलो काजी सर शेअरिंग स्टॉप केलं. हॅलो काजी सर.
I'm closing, but the PC is hang. Yeah, wait a minute. Yes, it's gone.
मॅडम ची स्क्रीन आहे. स्क्रीनवर प्रेझेंट करणार आहेत का? नसलं तर बोलतील की तोपर्यंत. हॅलो काजी सर, इज इट पॉसिबल? Hello. Otherwise, we have to remove yourself. You can join again.
Yes, sir. I have logged out, but what is the position there? In mobile, I am not looking.
1 minute.
Sir, you can remove that.
मी जॉईन करू का?
हाँ. Yes, ma'am. कवटेकर मॅम.
हा जॉईन करते sir.
ओके ओके ओके.
सर दिसतंय का?
हो तुम्ही
नाही
दिसता मॅडम.
व्हिडिओ चालू आहे.
शेअर स्क्रीन करा मॅडम.
शेअर स्क्रीन.
शेअर स्क्रीन केले ना, शेअर स्क्रीन नंतरच PDF हे केले. माझं हे दिसतंय का त्याच्यामध्ये?
प्रेझेंटेशन नाही दिसत अजून.
नाही दिसत का?
ते मिनिमाइज करा आणि शेअर स्क्रीन करा.
शेअर स्क्रीन
आता दिसतंय.
आता दिसायला लागले. आता तुमची PDF ओपन करा मॅडम.
केली की.
ओके
आता दिसतंय का?
येस येस.
Thank you, sir. The title of my research paper is on the first set Jn of alpha beta kx of biorthogonal polynomials suggested by the Jacobi polynomials. Madhekar and Thakre succeeded in constructing a pair of biorthogonal polynomials Jn of alpha beta kx and Kn of alpha beta kx, which are suggested by Jacobi polynomials. In the sense that for k equal to 1, both these polynomials reduces to Jacobi polynomials. Madhekar and Thakre obtained the recurrence relations, operational formulae also, generating functions also, and biorthogonality and multilinear and multilateral generating functions involving the biorthogonal polynomials suggested by the Jacobi polynomials. In this present paper, we have obtained some interesting results with some particular cases for the first set of Jn of alpha beta kx. Madhekar and Thakre constructed the following pair of polynomials, which is given here in the equation 1.1 and 1.2, in which Jn of alpha beta kx and Kn of alpha beta kx is there. They showed that the first set Jn of alpha beta kx is biorthogonal to the second set Kn of alpha beta kx with respect to the weight function 1 minus x raised to alpha into 1 plus x raised to beta over the interval -1 to 1, and where alpha beta are greater than -1 and k is positive integer. For k equal to 1, both the polynomials, that is Jn and Kn, they reduces to the Jacobi polynomials. Madhekar and Thakre obtained the biorthogonality, operational formulae, and generating functions of these polynomials. The polynomials Jn alpha beta kx and Kn alpha beta kx are related to Jn of alpha and Yn of alpha respectively by the following relations, which I have shown in the equation 1.3 and 1.4, where Zn alpha and Yn alpha are the Kornhauser biorthogonal polynomials. In the present paper, we obtained some more interesting results for the first set Jn of alpha beta kx, and some particular cases are also noted. The generalized hypergeometric function is given by the equation 2.1, in which PFQ, that is explained here, the equation for hypergeometric function, where P and Q are the positive integers or 0, alpha 1, alpha 2, alpha p, these are the numerator parameters, and beta 1, beta 2, beta q, these are the denominator parameters. Following the definition, which I have shown in 1.1, we easily observe that the polynomial Jn of alpha beta kx has the following hypergeometric representation, which I have explained in the equation 2.2. Then Chaundi gave the generating relation, which I have shown here in the equation 2.3. Specializing the parameters in the above equation, in the view of hypergeometric representation, we get the generating relation summation n from 0 to infinity lambda n upon 1 plus alpha kn Jn of alpha beta minus n kx t raised to n is equal to 1 minus t bracket raised to minus lambda k plus 1 fk, and this part which I have shown in the 2.4. Replacing x by 1 minus 2x by beta and using the relation 1.3, we obtain the generating function Zn alpha xk, which is obtained by Srivastava. Then replacing t upon lambda in the above formula and taking lambda raised to infinity, we get the following generating function, which is obtained by Madhekar and Thakre. Replacing x by 1 minus 2x and putting k equal to 1 in the above equation, means in equation 2.6, we get the non-generating function of Jacobi polynomials due to Srivastava and Joshi. Putting k equal to 1 in 2.6 and using Kummer's transformation, we get the Phleddem's formula, and which I have shown in the 2.8. Srivastava, now reversing the orders of the summation, we can get the equation 2.9 and replacing alpha by alpha minus kn and beta by beta minus n in above equation 2.9 and using the result due to Renville, we can get the equation 2.10. Specializing 2.3 in the view of 2.10, we get the following generating function for the polynomial Jn of alpha beta kx, which I have shown in the equation 2.11. For k equal to 1, the equation 2.11 will reduce to the generating function for Jacobi polynomials, which is given by Manocha, replacing t by t upon lambda and taking limit lambda raised to infinity, lambda tending to infinity. In the above equation 2.11, we will get the equation which I have shown here in the equation 2.13. Putting k equal to 1 in equation 2.13, it will reduce the following generating function, which I have shown here in the equation 2.14, and replacing t by minus t and alpha by beta and beta by alpha in the equation 2.14, we can obtain the result which I have shown here in the equation 2.15. Now using the result from the Renville, we can obtain the equation 2.16 and replacing x by minus x in the equation 2.16, we can get the equation which I have shown here in the 2.17. Now for the about the recurrence relation, consider the following formula from the Renville. From 2.2, we have d upon dx Jn of alpha beta kx is equal to d by dx in of 1 plus alpha kn upon n factorial k plus 1 fk, and this part. Using 3.1, we can get this equation. In the view of hypergeometric representation of Jn of alpha beta kx, we obtain the following recurrence relation, where capital D is equal to d upon dx. The equation 3.2 can be written as in this way, which I am showing here. It is not difficult to observe that 1 minus x raised to 1 minus k d raised to m is equal to Jn of alpha beta kx is equal to this RHS part, which I have shown here in the equation 3.3, where n greater than or equal to m greater than 0. For k equal to 1, the above equation 3.3 reduces to the result for Jacobi polynomials, which we can see this result in the Renville book also. Madekar and Thakre equation 16 and 17 obtained the following recurrence relation, which I have shown here in the 3.5 and 3.6. Eliminating x minus 1 d Jn of alpha beta kx from 3.5 and 3.6, we can easily obtain Jn of alpha beta kx is equal to k in the bracket 1 plus alpha plus nk minus k minus 1 Jn minus 1 alpha beta plus 1 kx plus Jn of alpha minus 1 beta plus 1 kx. Now using the 3.2 in equation 3.5, we can have this equation.
Hello, ma'am. Please
sir,
conclude yourself, ma'am.
Only 10 seconds, sir.
Okay. No problem. Okay, ma'am.
Replacing n by n plus 1 and beta by beta minus 1 in above equation, we can get this recurrence relation. And these are the references which I have used. Thank you, sir.
थँक्यू. अजून किती पार्टिसिपंट राहिलेत?
Hello, ma'am.
Hello.
Two to 3 participants are there, but due to connectivity, there is problem. We are turning towards valedictory function now.
Okay,
ma'am.
Really all
Sajne,
participants presented.
Sajne, ma'am.
Myself, Sajne, madam.
Yes.
Really, all participants presented their paper very well, because it is difficult to present research work within 4 to 5 minutes, and really they tried very well.
Yes, ma'am. Yes.
Thank you to all.
Okay. Thank you, ma'am. Now, head of the department, Salunke madam, will deliver vote of thanks for all this national conference towards Salunke ma'am, HOD, Department of Mathematics, DP Bhosle College, Koregaon.
all of you. Good evening to all of you, respected dignitaries, faculty, students, researchers, and all participants in today's national conference on recent trends in mathematics and statistics by DP Bhosle College, Koregaon. Here, I am Salunke, Head Department of Mathematics, coordinate of this national conference. I feel honored to privilege to get the opportunity to propose the vote of thanks on this special occasion. I would like to thank today's chief guest, Honorable P.S. Patil, Vice Chancellor, Shivaji University, Kolhapur. He delivered a keynote address for today's conference. Thank you for your valuable guidance. I extend my thanks to today's event president, Dr. C.D. Lokhande, Director, CIR D.Y. Patil University, Kolhapur. Thank you, sir, for your informative lecture. I am very thankful to Dr. M.T. Gopne, sir, by delivering a nice lecture on forbidden lattices, partial reducive lattices, graphical representation. Very nice lecture, sir, which is very useful to all researchers and the students. I am also thankful to Dr. Sachin Kumar Bhalekar, sir, the young scientist from Hyderabad University, for valuable guidance on analysis of functional order delay differential equations, stability analysis, bifurcation scenarios, which is very useful to all the students and researchers. I am also very thankful to Dr. M.T. Bhute, sir, Head Department of Statistics, University of Solapur. He delivered a very nice lecture, which is the monitoring mean and variability by auxiliary information based control charts using Run's rules. I am very thankful to you, sir. I express my thanks to Honorable Principal Dr. P.S. Sawant, sir, who motivate us to and also guide to conduct the national conference. Thank you, sir, for your kind support and being with us. I am also thankful to all teachers, non-teaching staff, and also for all continuously with us. I am also thankful to chairpersons, Dr. Phadtare sir, Suknekar sir, Patil madam, Sajne madam, and Padade sir. I am very thankful to chair the sessions. I am also thankful to K.S. Jadhav sir, D.D. Patil sir, Maner sir, Koshti sir, and all teaching and non-teaching staff who help to this conference. I am also thank you for all the participants and the students who are together with this conference. Lastly, I am very thankful to all paper presentations given the research students, staff, and the researchers. I am also thankful to all the staff, teaching, non-teaching participants, and those who are remained to give the vote of thanks. And with the kind permission of the event president of this organization, this session is over. Thank you. Thank you very much. Now the feedback. The feedback link will be sent tomorrow, and the certificates will be after 4 to 5 days later. Thank you. Thank you very much.